Jagabandhu, Jagabandhu, unable to hear you. Shall we start, Jagabandhu? Lalaram? Lalaram?
Hello, am I audible now, sir?
Yes, yes. Shall we start?
Yes, sir.
Yes, sir. Yes,
Okay.
sir. Yes, sir.
Okay, thank you. So,
Yes, sir. Hello.
yeah. Able to hear me?
Yes, sir.
Yes.
Yes, sir.
Shall we start?
Yes, sir. Yes, sir.
Yes.
Yes, sir. Yes, sir.
Okay. So, good afternoon to everyone. Welcome to this GYAN course on cognitive speech processing. My very early morning to my foreign colleague, Professor Rufinar from Argentina, who will be handling most of the lectures for this course. And I will be doing some of the complementary materials required for his course. So in this introductory lecture, of course, the course will be formally started by Professor Rufinar at 3:30 p.m. 3 to 3:30 we will have the inaugural. But what I felt was I wanted to give a big picture of the cognitive speech processing area, where, of course, since it is about 10-15 lectures by Professor Rufinar, about 15 lectures, he will not be able to cover the whole thing. Second thing is, since most of us are working in the speech processing area, which may not be directly uh, working from a cognitive perspective, that is where I felt it may be a good idea to um, give some linkage between what is the focus that is happening in the cognitive speech processing area versus what is that we do in the unless specified the standard speech processing area. Of course, once I saw this, there are plenty of research articles I was able to just browse through. Most of the content for this introductory lecture I have taken from this first reference by Milos Sarnak and et al., Cognitive Speech Coding, which has come recently in IEEE Signal Processing magazine in 2018. Of course, when I went just browsing through from the references of this article and others, there are a lot of activities that are happening over decades uh, in this domain of cognitive speech processing. Of course, as a community working in the speech processing for different applications, we were focusing in something else direction, essentially to build speech technologies useful as an application domain. Assume that I record the acoustic signal using a microphone, then how do I process that to do any of those tasks? That is what we were focusing. But the cognitive speech processing was focusing on certain aspects which are complementary to what the application area that we were looking. With the recent advances in deep learning, looks like there is possibility for overlap among these two areas. At least we can benefit from each other. So in that direction, when I requested Professor Rufinar, can we form a course on this? he had kindly agreed, and because since his group working in this brain-computer interface for last many years, they have done some very good work. So in that direction, he has kindly agreed. With that, this course has been formulated. Of course, I suggest these articles are available in the public domain. I suggest you people to download, and from their reference, you can go and try to do it. Then I organized my thoughts for this talk in the following way. I want to give a brief introduction to this speech processing area. Then I would like to highlight the distinction between the focus that we do in speech processing area versus what is called this cognitive speech processing. When I go to cognitive speech processing area, broadly when I see there are, I think, three directions at this point of time I am able to discover. One is the temporal processing by the cognitive speech processing. Temporal processing that is happening in the human brain. That is one phenomenon which has been demonstrated by the study of auditory cortex in the human brain for processing the speech signal, which we seem to be not exploiting in the speech processing area that much. Because we are dominated by the spectral processing of speech. So as a result of that, so I felt this temporal processing is one concept which has been shown to work very well by studying in the cognitive speech processing area, can be one take home which we can use it for speech processing area. The second concept is what is called the sparse processing that happens in the auditory cortex. So that means to say, in a layman term, if there are so many neurons in an auditory cortex, only a small fraction of those neurons will fire at any point of time when acoustic stimuli is received to that part. So that means to say, majority of the neurons will not be firing, only few of them will be firing. So accordingly, it also gives us a direction for the research where I can have a very large dimension vector in which only few dimensions will be non-zeros and rest of them are. That is the sparse processing what we are talking. That also seemed to be the reason of that is how it is happening in the auditory cortex. That concept also can be taken into the conventional speech processing area. One more part is I did not mention here. That is another one is what is called a layered way of processing this acoustic stimuli to arrive at the whatever the concept that we are going to comprehend from the speech. That is deep structures. Layered way processing that is also can be exploited. That is being exploited by the deep learning now. So that is also another concept which is coming from the cognitive speech processing area. At least we can try to relate that. Then I'll explain about some one functional model. There are many models. One functional model of cognitive speech processing inspired from cognitive speech processing for the speech processing area. Also, in the conventional speech processing area, as well as inspired by the cognitive speech processing, there are many attempts that have been made to make use of this biologically inspired knowledge in developing some of the speech tasks. As an example, one or two cases I will take and try to illustrate that how they have benefited from this, which gives us clue for in our own direction of research. And also the concept of spectrotemporal features. Of course, as if we are working in the speech processing area, we have this spectrogram. We seem to be using earlier mainly for visual representation of speech. Now, for the last few years, people started using it as a raw representation of the signal to train deep neural networks. So this also can be linked to the concepts that are put forward in the cognitive speech processing area, that the spectrotemporal way of viewing will give us a better discrimination among different sounds or long-term concepts in the speech processing area compared to a one-dimensional time domain processing or frequency domain processing that you are trying to do. Then I will summarize my talk. Of course, if we see into the literature of cognitive speech processing, one of the major factor that was driving this area was to understand why this human auditory system, which is endowed with all of us, performs more robust than an automatic speech processing system that we have built to work on a computing machine. This was a very challenging question and intriguing question for all working in the speech processing area, because of course now with the deep learning in the last few years, at least in some of the tasks, the performance is comparable to that of humans, but only for that application and that context. Okay, even without, still a long way to go to see um, how humans do it, and we try to interpret that. But however, more than this, for a long time, this has inspired generation of researchers working in the area of brain and auditory processing, that all of us, we witness on a daily basis the way we can comprehend information from the speech signal from a very highly noisy environment is a testimony for this. The human auditory system is very robust for any of the external degradations, and then how that human brain is able to do such a thing. So that was the question that that has driven the generation of researchers to in the cognitive speech processing area. Of course, when we are coming from this direction of conventional speech processing, we have to some extent understood, or to a very large extent, we have understood the speech production area, speech production concept, speech perception concept. Now we need to distinguish the speech perception with reference to cognitive speech processing. Essentially, how to distinguish between speech perception versus cognitive speech processing. So that should be our approach, so that we can see how the efforts that are made in the cognitive speech processing area are quite distinct compared to some of the perception concepts that we use in the speech processing area. Just to tell, I think some of you have seen the Fundamentals of Speech Recognition book by Rabindranath Jang. In one of the introductory chapter, he mentions that, of course, I'll do that in the tomorrow's lecture, that if we look from human-human communication point of view, that human cognitive processing, the information rate it at a very low rate, roughly, just for example's sake, we can say about 50 bits per second. Of course, there is no great significance for this 50 bits. Essentially, few tens of bits are sufficient. On that basic idea that suppose if you have 32 phonemes in a language, these 32 phonemes I can code using 2 to the power of 5, 32 bits. 5 bits is sufficient. Plus, roughly you can generate about 10 phonemes per second. On that basis, 10 into 5, 50 bits per second. If you look from a spoken language communication point of view, human-human communication, if I want to decipher the information rate, what is present in that is only at about 50 bits per second. Okay, that is the rate at which our human cognitive system looks for decoding the message. Alternatively, any of our speech processing techniques that we consider, whether you consider automatic speech recognition, speaker recognition, language identification, speech coding, any of those things, name it, they are based either on production or perception, and they operate at much higher rate. For example, if you consider a 16 kilohertz sample signal with 8 bits for each sample, you're talking about 128,000 bits per second, 128 kbps. Even if you reduce the sampling rate to 8,000 hertz, it will be 64 kilobits per second. 64 kilobits per second, much higher than 50 bits per second, what human cognitive system is able to process. So what it says is, our human cognitive system is able to decipher the information which is present at a very low rate. However, since we have not understood how exactly our cognitive system does this, we have mimicked that by using the other knowledge available in terms of speech production or speech perception. And to ensure higher accuracy, to deal with external disturbances, we have increased the data rate to a much higher rate, so that there is a lot of redundancy in the data, so that I will not be losing much information. But this target, one of the striking points cognitive speech processing says is, you can build a speech processing system at a much lower data rate, giving very good performance. So that is the take-home message from the cognitive speech processing area. Though that is where one of the questions we can put when I want to work in the cognitive speech processing area: can I reduce the data rate further by exploiting some of the cognitive speech processing concepts? That's where the cognitive speech coding research article is there. And not only for that, even for storage point of view, all those things. Can I reduce the data rate by exploiting this cognitive speech processing? Second thing is, can we bring more robustness to different automatic speech processing systems? Because whether we want it or not, we have humans as reference when it comes to the spoken mode of communication. And as humans, we have a very robust way of communicating using speech mode. So we want to give that robustness to automatic speech processing systems also. For how to bring robustness to this automatic speech processing system, again, for that also, we can take inputs, some of the findings from the cognitive speech processing. Then the next third dimension for this cognitive speech processing is, there are, of course, the task that we are performing as of now, trying to build automatic speech processing systems like automatic speech recognition, speaker recognition, LID, language identification, and so on. Compared to that, there are many more challenging tasks which are cognitively effortless for humans, but difficult to implement. We are clueless on the conventional pipeline of developing systems. For example, you might have heard about what is called the cocktail party effect. That means to say, when I go to a very noisy place, for example, you're going for a dinner party or something, as soon as you enter that gathering, you feel that it is so noisy. It's a chaos place. Okay, you feel like, oh, how do I communicate? But quickly, within few minutes, you will yourself regroup into a smaller subgroup with your friends and start communicating with them at the same level, Of course, if you selectively pay attention to listen to that chaos, you can listen, but otherwise there is no problem for communicating with the fellow friends who are there in the party. This is a very hallmark ability of human cognitive system. Then how cognitively it is effortless, but it is very difficult to implement. So how do I bring that knowledge in building automatic like this? At least I found by looking into the literature 3 different directions which are relevant for us. One is reducing the data rate. Second one is adding more robustness. Third one is coming up with new tasks which are cognitively effortless but difficult, which are much harder than conventional speech recognition, speaker recognition, and so on. So the first thing is, when I say cognitive processing, we need to distinguish this with reference to the speech perception that we have studied. I'll do it in the next 2 slides. Essentially, it refers to the information processing in the central nervous system after the peripheral auditory system. So peripheral auditor means this ear we have as a sensor for collecting the acoustic signal. When the signal passes through the ear and gets onto the auditory nerve fiber, and when it reaches the brain, in the brain, all the activities that are happening, that we group under what is called cognitive processing. Of course, as I mentioned in the opening remark, neuroscience-based studies are there for several decades to understand more about how this speech production is happening, perception is happening, comprehension is happening from a central nervous system point of view. Okay, and they have developed many models based on this for automatic speech processing. Even though many of us working in the conventional speech processing area do not pay attention, but there are enough directions which they have put forward, which some of them may be put into our use. Okay, so this point I have already mentioned. Even though we don't know, still it is a difficult gray area to understand how and why it is happening inside the human brain. However, as humans, we are all witness to this experience, that we agree that we have a very robust way of communication, and also we do many tasks apart from message transmission to the fellow being. Many other things we can do by the speech mode of communication, which can be attributed to the cognitive part, which we may not have understood at this point of time, but research is going on in that direction. This picture taken from this, again, the 2018 paper, will give us some direction, feel for what is the focus in the cognitive speech processing area. One is, we have done, you record the time domain signal like this continuous signal. Then you segment into smaller frames, each chunks 20 milliseconds with a shift of 10 milliseconds. And you can process in the time domain itself to derive certain information like short-term energy, autocorrelation, zero crossing rate, and many other things by time domain processing to know more about the nature of the signal. But if you see what is the hallmark of this one means, one is this nature of the waveform is speaker sensitive, because it's a speaker dependent nature of oscillations, variation, and it is also sensitive to speech rate. A person can produce faster or slower. So all that information is available in this one. So accordingly, whenever I am developing speech signal processing methods to process this acoustic signal, they are affected by these factors. We have mentioned these 2 aspects, but many other aspects. The next thing is, when this acoustic signal is fed to the human ear, we have 3 portions in the human ear. The important part is as a part of inner ear, what is called cochlea. And if you see, generally, it is a well understood concept studying this cochlea by the neuroscience community, that it gives us something what we call a spectrotemporal representation, segregation of this time domain signal that is fed into the cochlea or inner ear. Typically, we can assume it to be something like this. An auditory spectrogram is generated, and this auditory spectrogram information is coded onto the auditory nerve fiber and then goes into the human brain, and that is essentially goes into the auditory cortex portion, and the rest of the processing happens there. So up to this point, we have understood that is now how spectrotemporal representation happens. And many of, based on the study of the structure and functioning of the cochlea, there are perceptually motivated signal processing methods have been developed. All of us know the well-known Mel filter bank, gamma tone filter bank, and many other things. Perceptually motivated signal processing concepts have been developed. But nothing beyond that. Once it goes beyond this auditory nerve fiber, what happens in the auditory cortex, that is not the domain of the speech perception that we are aware of. The concept of speech perception that we are studying as of now will be essentially ends with this cochlea functioning. Essentially, this spectrotemporal representation construction in the cochlea, that is where our story ends. Rest of the things that is happening in the auditory cortex is the domain of cognitive speech processing. One of the things they have marked here in the spectrogram bottom, if you see, these small regions represent the phonemic variations or phonetic variations that are there. Then the larger duration variations, they are like syllable variations or prosodic variations like this. So all this level of information is available in the spectrotemporal representation, but when we do in the conventional speech processing, we don't really have an approach to do such fine level segregation of the spectrotemporal representation at multi-scale, okay, to derive the information. But what is found is auditory cortex is able to do that. Essentially, as a result of exploiting such variations that are there in the spectrotemporal representation, it finally gives out in the form of a discrete representation sequence of phonemes. And what is important is it is speaker insensitive. You can see when I go for either time domain analysis or spectrotemporal representation by perceptually motivated filter bank, it is mostly still affected by speaker sensitive or speech rate sensitive. But when it goes into the auditory function, it becomes speaker insensitive and speech rate insensitive. So that is the advantage of cognitive speech processing. So if we want to provide robustness to the speech processing systems, it should deal with different time scales, which one scale may be very finer scale frame for maybe phonemic variations, next higher level scaling for syllabic variation, and a very larger time scale for a prosodic temporal modulations. For the same spectrotemporal representation, human cognitive system, that is auditory cortex, is able to view, chunk the given spectrotemporal representation at different levels. One for phonemic level, one for syllabic level, another for prosodic temporal modulation, and then exploit them to do the required robust way of processing the information. So that is where the advantage of studying the cognitive speech processing comes into picture. These concepts, this multi-time scale thing, which we have not exploited so far, can indeed be exploited by going deeper into the cognitive speech processing area. Just to some figures I have taken from the public domain. If you see, all of us, when we listen to the speech signal, this through the ear, which in the tomorrow's class I will tell more about this ear mechanism, all those things. From there it reaches the auditory cortex. And this auditory cortex, all that further processing happens to discover the information that is there. If you see from a back view, from the acoustic variation that are coming, this is ear canal representing the outer ear. Till this end point of the outer ear, acoustic pressure variations will be coming. At the end of the outer ear, I have that eardrum. This eardrum will convert this acoustic variation to mechanical variations, and these mechanical variations are transferred through a set of bones which are there in the middle here, this yellow color, and then that gives a fluid motion inside this. This is the cochlea. From the cochlea, this auditory nerve goes, and like this, from the left ear and right ear, that knowledge comes, and these are channeled to the auditory cortex, left hemisphere and right hemisphere. And these are the auditory cortex portion where this information coming will be further processed to derive the message. So that is what happens. And the goal, what we have studied so far, will end here, that cochlea. That's what I mentioned in the. Whereas in the cognitive speech processing, we are focusing on what is happening in this auditory cortex area, this portion and this portion. Okay, that is the focus of auditory cognitive speech processing. Again, this is the auditory pathway, how it goes. From the auditory nerve, it goes through and terminates in the primary auditory area in the cerebral cortex. And in the region around this, how the neuronal firing is happening and how that can be recorded and decoded for getting the information. So that will be the focus of cognitive speech processing. That's what you're going to study in this week course. For example, if you question what is done till now in the speech processing area, we have well understood the speech production knowledge. Literature is there for a long time, centuries. People have built mechanical model, electronics model, software models for speech production. For example, the well-known LP analysis is the result of understanding the speech production mechanism. Similarly, we have exploited the knowledge of speech perception that is happening in the ear, that is peripheral auditory system. As a result of that, many perceptually motivated concepts have been proposed. One of them is the MEL filter. Now, when we see the acoustic signal entering into the human ear, the first stage of acoustic treatment happens in the peripheral auditory system, that is front end, which is nothing but the ear. In the layman term, it is the ear, which includes outer ear, middle ear, and inner ear. Before reaching the auditory cortex, is well characterized. When you say what is being well characterized so far, the human ear functioning, that is up to conversion of given one-dimensional signal into a two-dimensional spectrotemporal variations and coding them onto the auditory nerve fiber, that part is well known. That is till you reach the entry point of the auditory cortex. Beyond that, what happens in the auditory cortex is not the domain of peripheral auditory system, and the concept of perception accordingly, what we are referring is only to the peripheral auditory system. Okay, we'll do not focus not much on what happens in the auditory cortex, and that is exactly the domain of cognitive speech processing that we are going to study. It is difficult as the different units will be there in the speech signal, where they are organized in the form of phonemes, sequence of syllables, prosodic information, prosodic different levels like stress, accent, intonation, many prosodic information will be there. All these things as a complex band, it is available when I get into the spectrotemporal representation. So that one, and they are occurring at different time scales. Then how to deal with that is a very complex phenomenon, but the human auditory system is doing in a very effortless manner. So thus, the stages that involve auditory cortex and other cortices around them are the subject of cognitive speech processing intense research. Of course, as a neuroscientist, they do that, and they put forward their findings. From that, can I do some speech processing? So that is where our focus comes from an engineering point of view. Even though as a neuroscientist, we may not go and do a invasive approach to record the EEG signals or responses from the neurons, but at least in a non-invasive manner, we can take the EEG data collected from the head and process them to interpret some of the information related to the speech, maybe phonemic information, syllabic information, or prosodic information, and so on. So just, I said many times, but let me repeat one more time. If I want to differentiate between speech perception versus cognitive speech processing, for us, coming from conventional speech processing area, the speech perception, unless specified, is mostly limited to what is happening inside our human ear, or specifically that cochlea, or what we call it as peripheral auditory system. From a cognitive point of view, they all call this as peripheral auditory system. Alternatively, cognitive speech processing will be focusing on the phenomenon that is happening in the auditory cortex and associated cortices. Okay. The concept of speech perception based on the peripheral auditory processing, that is what is happening in the cochlea, is extensively studied in general auditory and speech processing. That's where your perceptual audio codecs or perceptually motivated filter banks, so many things have come. Biologically, not only the cochlea, but the whole auditory cortex contributes to speech perception. Okay. The auditory sensations that we all experience when we are doing spoken mode of communication will reach that perception level only if it is received and processed by the cortical area. Okay. If your cortical area is not working, even though your ear is there, able to do spectrotemporal conversion, if the auditory cortex is not functioning properly, then there is no way of perceiving that information. However, we have limited only perception means what is happening inside the cochlea or peripheral. But in the cognitive speech processing, we are going beyond that. That's what I. So accordingly, we need to record the responses from the neurons which are there in the human brain and relate them to the speech signals. This I mentioned that when it comes to cognitive speech processing, one of the important phenomenon that they have put forward is what is called temporal aspects of speech processing. By that I mean, when I consider the speech signal, the information in the speech signal lies at different time scales. Okay. For example, there are cortical oscillation, that is nothing but a group of neurons. They will be oscillating at a rate of 1 to 2 hertz per second, or 1 to 2 hertz. That means to say 1 or 2 oscillations per second will be happening. And these can be attributed to some of the long-term, slowly varying information, like prosodic information. It is an intonation, accent, a stress, like that. Those are a set of neurons will be generating these oscillations at the range of this 1 to 2 hertz. Similarly, there are a group of neurons which are oscillating at 3 to 8 hertz range, which indicates that roughly you have 3 to 8 syllables per second. And there are oscillations at the range from 25 to 35 or 40 hertz, which are encoding the transient acoustic properties. It is not that phonemes, but the phoneme itself, if you see, roughly I told about 10 phonemes per second. Each phoneme will have 3-4 transient acoustic properties. Okay, there is a closure bar, burst, transition region, and so on. So 3-4 if you code, then 10 into 3-4, 30 to 40 transient phenomenon that are happening. There is a separate group of neurons that will be oscillating for this to decode them. So you can see the same spectrotemporal information which is fed as input to the auditory cortex will be processed in parallel by a separate group of neurons, one operating at 1 to 2 hertz, another group operating at 3 to 8 hertz, yet another group operating at 25 to 40 hertz, to decode different aspects of the speech information. Of course, they may be combining there later, depending on the requirement, to give that robustness to the perception. So that means to say, one of the important phenomenon as a byproduct of this cognitive speech processing is, how do I process the speech signal at different time scales? And since our human cognitive system seems to be benefiting well, then how do I mimic that activity on a conventional speech processing area? Then the other one is, even though separate groups are there or something, it always ensures that as humans, maximum information is conveyed to the brain, okay, while minimizing required energy and neural resources. So this is very important. All of us, and jokingly, if we say, um, we can speak for hours together without much effort. Okay. Uh, what I mean to say, of course, if you speak for hours together, you may get tired. But in general, if you conserve your energy and speak at a normal level, you can continue to speak for a long time. You can imagine that you don't spend much energy. Vis-a-vis, if you are doing a exercise, physical exercise, you will be quickly exhausted. Okay, you can see that um, the beauty of human cognitive system is in all difficult external scenario, external degrading acoustic backgrounds or something. In spite of that, it ensures that the maximum information transfer takes place from the auditory nerve to the perception level. At the same time, it conserves the energy. Also, it is not that all the neurons are utilized for the whole thing. What has been found in this electrophysiological recordings is no more than 5% of the neurons of the auditory cortex fire for any acoustic stimulation. That means to say a very small group of neurons are fired at any point of time. As a result of that, you have a large number of neurons available for parallel decoding of other information. Okay. So accordingly, we can say that suppose assume that I have just for example, there are a large millions of neurons in the auditory cortex. Each neuron output I put it as one dimension in that 1 million vector. Only 5% means maybe less than 0.05 million of neurons are fired at any point of time. That means to say it's a very sparse vector. Okay, this sparse and highly selective is maybe the cause for the accurate representation and better discrimination among different information sources that are there in the given speech signal. Okay, so that this sparse coding is also another important concept, maybe related to the robustness that is there in the human cognitive processing area. Similarly, if I take it's a layered architecture. The hierarchical processing will be happening through several layers in the auditory cortex. That is also another central phenomenon that happens in the auditory cortex. Okay, so thus the principles of this temporal processing, sparse representation, and hierarchical structure in the auditory cortex in representation learning of the sound are can be used for the future of speech processing. Okay, so that is these three are the important concepts that we can readily take from the cognitive speech processing area and use it in some of the speech processing tasks to arrive at an improved performance. So I think this is one model. Of course, there are many models. One of the functional models that have been proposed for human speech processing is the following way, where when you get these sounds, that is acoustic signal, this is the peripheral auditory system. Okay, what that happens through cochlea, outer ear, middle ear, and inner ear, and till the entry point of the auditory cortex. Okay, so this is what we have studied as a part of speech perception system or something so far. Now, the other component that we are going to add when we are including this cognitive speech processing is there is a central nervous system activity to complete the speech perception process. For example, the auditory speech perception, that what happens in the auditory cortex, can be treated as two main broad activities. One is the spectrotemporal analysis, means analyzing the information coming in a spectrotemporal way to chunk it at different time levels. One sequence, one chunking required for phonemic level, another chunking required for syllabic level, The third one requiring for the suprasegmental or prosodic level. And then also this phonological framework, just to put those sequence of sound units together to form a meaningful phonological encoding that makes sense for us. Okay, so those are the phenomena that is happening in the background of the core of the auditory cortex, and that will be used maybe either for speech production or for the speech recognition from the auditory cortex. If I want to generate speech, again I use this knowledge which is happening in the back end to complete this process, either for the production or for the recognition of the message. That's why the dorsal stream they call, and the ventral time is now the name, we need not worry. The dorsal, which is also called as back or posterior stream of speech production, and the ventral is nothing but the front or anterior stream of speech production, recognition and understanding. Okay, so this is one of the dual channel cognitive speech processing model, they say. If you see this, we were mostly ending at this point for perceptually motivated filter bank. We are also adding that additional component depicting the functionalities that are happening in the auditory cortex. Okay, so that is what is the model motivated from the cognitive speech processing. If you see the temporal organization of the speech, pictorially it can be illustrated like this. The structured or accented thing will happen at a very poor resolution time scale. That's why this time scale is very big. The next lower level, 3 to 8 hertz or 3 to 8 oscillations per second, comes this syllabic. Next lower is phonetic, which is lower, several phonetic units together constitute a syllabic. And phonological, which is more at an abstract concept of language and the arrangement of sounds in the language, valid sounds in the language. So all those things which are more at a much finer scale, which are there in the temporal. So this is the way at which it will decompose the spectral representation and makes out of the information. So there are many attempts people have made to study the structure and functioning of the auditory cortex and other parts of the human brain from a speech processing point of view, and came up with several biologically inspired systems. Essentially, the goal was to enhance representation and modeling of speech. And for example, few cases I have considered. So here, the models that they proposed, motivated from or biologically inspired from the structure and functioning of the human brain, these models approximate the peripheral and the central auditory system with a very large dimension vector. Okay, so that is what the purpose. Very few examples I have taken. Many more are there if you go into the literature, which I can explain. For example, this is one good example to distinguish or appreciate a task which is cognitively effortless, whereas difficult to implement on a computing machine. For example, very simple mechanism, classifying machine-generated versus natural noise sources using cortical representations. All of us, we can quickly recall, suppose if I am listening to a fan noise or listening to a computer noise or any aeroplane noise or a car noise, these are all machine-generated noise versus the natural noise sources that are there in the environment, bird chirping or some other natural, the water waves in the seashore when we stand in the seashore. These are all natural variations. As humans, we have no problem in distinguishing these two broad categories. Okay, but it's a very hard task. That is a very fine cognitive task we are doing. Very difficult on a computing machine to do that. Okay, and that is what I meant. We can think of developing such systems which are And these have several applications. Suppose if I'm getting incoming noise, generally, as of now, we do all noise into one category. But assume that I need an application where I need to segregate those noises into multiple levels. It becomes harder. So that is where we pull all of them into one category. But on the other hand, if I want to pull them into different categories, how to do that? And one of the work I will explain in the next slide, they have shown that by exploiting these cortical representations, they can indeed do much better job compared to the conventional short-term processing. Similarly, a speech analysis model is proposed based on the model of the central auditory system. And neuromorphic based oscillatory devices have been developed for incremental syllable boundary detection. These are a few examples, but many more things are. For example, if I go for classifying this machine generated versus natural noise, if you consider the existing focus, what we do in our conventional signal processing area, what we call content-based audio classification, we develop techniques which will focus on classifying the events which are both semantically and perceptually distinct. And when I say content-based audio classification, I assume that different audio categories are semantically and perceptually distinct. For example, speech and music both are audio signals, but speech and music are quite distinct. Okay, and that is what is the focus of content. If they are quite distinct, even though they are audio signals, since they are perceptually distinct, semantically distinct, I can develop automatic systems to classify them without much effort. Alternatively, it will be challenging to distinguish between the different categories which are semantically and perceptually close. For example, machine generated versus natural noise sources. Okay, so in this work, what the authors have done is they have developed a bio-inspired tensor representation of idea. So tensor representation of a very large dimension tensor, which is a three-dimensional matrix-like thing, which will model the processing, what happens at the auditory cortex for feature extraction. I can say a multi-dimensional and a large dimension feature vector has been developed, and using that they have developed this classification system, and it has been shown that the result of this auditory perception, this cortical perception, auditory cortex based feature extraction method seem to be giving significantly better performance compared to the standard MFCC features that we use in the conventional peripherally auditory perception based system. Similarly, when I go for a speech analysis in a model of the central auditory system, they have the motivation for that work was a computational model of the mammalian central auditory system is adopted to analyze and interpret a data redundant and dimension expanded representation. So it is it's a counterintuitive at that point of time when they proposed it in 2007. So there we are always reducing the dimension of the vector so that the dimension of the vector becomes less. Whereas here it is exactly in the opposite way. We need a very large dimension vector, okay, such that I exploit that sparsity concept that is there in the cortical processing, and using that I can have come up with this large dimension vector and use that for any particular task. Essentially, what the central auditory system, where each neuron is specifically tuned for a particular frequency and particular intensity, then you can put a large dimension tensor to have a placeholder for each of those neurons. And then for a specific event, only a subset of those neurons will fire. So accordingly, it will become more distinct. Because on the other hand, if you have brought it to lower dimension, everything would have been smoothed out. So that is the very purpose. And they have shown that for a speech recognition task, this model gives better performance compared to that. Similarly, the spectrotemporal features, spectrotemporal modulations have been shown to play an important role in sound perception. That means to say, don't just take a small segment of 20 millisecond and process it either in the time or frequency domain. You take a chunk of spectrotemporal region for processing the information. One of the piece of the work done by Vikram for his PhD. Of course, this is a very crude way, but it sends the message where if I have a oval onset point, you take a small region around that and take the entire spectrotemporal region and extract the two-dimensional discrete cosine transforms. So that is what has been done to identify, is essentially constitute the consonant to vowel transition region. And I do two-dimensional processing, spectrotemporal processing, and which is used for classifying normal versus misarticulated stop classifiers. So there, of course, compared to this, I will show you this. For example, if I take an MFCC, which is a short-term processing version, and if I want to compare with normal versus misarticulated sounds, two-dimensional DCT1, the single pole filter based two-dimensional DCT1 gives much better performance compared to short-term Fourier transform based thing, compared to this conventional short-term processing by MFCC. It indicates that no, when I do the spectrotemporal based processing and use it, earlier we were not doing because of the difficulty in handling the two-dimensional data, but now with the computing resources, if I go by the two-dimensional processing, we will be able to do much better. Of course, some other results are there. I think I'll just finalize. These are some of the features. Just to summarize, what I have just give a glimpse of the impact of this cognitive speech processing area in automatic speech and audio processing. And I try to bring out some important concepts from human cognitive speech processing and some of the important properties of cognitive speech processing, which essentially refers to this temporal processing, sparse processing, and deep structures in the auditory cortex. So this deep learning and neural basis of speech and language processing have tremendously advanced recently. So many of these findings can be used for speech representation, learning, and pattern processing, especially now when we are applying raw spectrogram as input to the deep learning network, and it goes through several layers and gives us some smoothed version as we move up from one layer to the other layer. If I want to interpret what is happening, we can take shelter from many of the findings that are there in the cognitive speech processing. There mostly that visual representation comes. For the different tasks, can I have the representations obtained from cognitive speech processing to interpret what goes? So in that way, so focusing on this cognitive speech processing area will have many advantages at this point of time, thanks to the technological trends that are available, both in terms of GPU computing and large amount of digital speech that is available, and it's also becoming easier to collect the EEG data. I think with that I will stop here. I think we have to thank you for the listening. If you have any questions, I'll be very happy to take up. Any of you?
Good afternoon, everybody.
Yeah, good afternoon, sir. So, I think 3 p.m. Sheshu sir is. So we'll start the. So sir, just waiting.
Hello.
Yes, please.
Yes, sir. Am I audible?
Yes, please.
Sir, I had this doubt that when we go to CSP domain, why the information becomes speaker insensitive and rate insensitive? Isn't that information still?
Maybe see, for example, when I go for this sparse encoding of the data in the neuronal system, no. Mm-hmm. So that learning by the neurons may be in such a way that it will only fire for that message component rather than the finer variations that are there in the speaker components. Okay. Maybe that may be the reason.
Okay.
Yeah.
Yeah, thank you, sir.
Thank you.
And so one more doubt was there. Like if we have, earlier we are telling that CSP is focusing on low bit rate processing, like 50 bits per second. And then because of original signal processing is much higher, like 128 kbps. But here also when we go for higher dimension tensor, isn't it equivalent to increasing bitrate again internally?
That is there, but
Yes, sir.
initial for representation point of view, we go to that higher dimension vector.
Okay. Okay.
But from that, ultimate information that we are trying to decode is only at that 50 bits per
50
second.
bits. Okay. Okay.
Just as
Internally, we are going higher. Okay.
the intermediate representation, we may go to a large dimension vector and try to.
For sparseness, is it for sparseness that
Yes,
you
mainly
meant
for
to
the sparseness purpose. Yeah,
Okay, thank you so much, sir.
thank you. I just check. So Professor Sheshu sir will be joining in few minutes. Maybe we will start the this inaugural thing. Then I think meanwhile he will join.
Sure.
Thank you all for enrolling yourself for this GAN course on cognitive speech processing. This is a very upcoming research area, especially in India, even though in abroad universities it is happening for a long time. We thought, no, we can give an exposure to this. I think Cheshire also has joined. Exposure to this for some of the research community in India. So in that regard, I had a discussion with Professor Rufinar and organized this course. And more about this I will tell. To begin with, I will request Dr. Amar Gaonkar, who is the coordinator for the GAN courses from IIT Dharwad, to give a brief information about this GAN courses.
Okay. Thank you, Professor Prasanna. I am Dr. Amar Gaonkar, a local coordinator of a GAN program at IIT Dharwad. Welcomes all the participants. Global Initiative of Academic Networks, in abbreviation GAN, is a program initiated by Union Cabinet, Government of India in November 2015. This program aims at tapping the talent pool of scientists and entrepreneurs internationally to engage with the institutes of higher education in India, such as IITs, IIMs, central universities, etc., so as to augment the country's existing academic resources, accelerate the pace of quality reforms, and further strengthen the India's scientific and technological capabilities. GAN is implemented to incorporate world-class faculty to teach in India. This initiative successfully garnering the best international experience into our system of education by bringing in global exposure for our students while being in India. Till date, there are around 2,101 GAN courses have been approved. Out of this, 1,603 are completed. This GAN course, that is a cognitive speech processing, is from the GAN phase 3, and the nodal coordinator or the national coordinator for this GAN phase 3 is IIT Kharagpur. I again welcomes you all this for GAN course. I now call Professor Prasanna to brief about this GAN course. Thank you.
Thank you, Dr. Amar, for all your efforts in securing these courses to IIT Dharwad. Of course, as I briefly mentioned in the introductory talk, this is a very upcoming research area. That too, the government of India has taken this area very seriously for the last at least 6-7 years. They have started a new direction for research, what is called Cognitive Science Research Initiative from the Department of Science and Technology. And they have started funding many project activities under this scheme, both individual R&D projects as well as consortium mode projects across the different institutes. So, of course, any interested participants can Google what is called Cognitive Science Research Initiative. Which is given by Government of India, and they have funded many projects across the country because they want to develop critical mass in the country to work in cognitive science area. That is one. So, of course, one of the important application areas of cognitive science is speech and audio processing as well as language processing. So in that direction, participants coming from speech and audio processing will be able to significantly benefit by knowing more about this cognitive speech processing. As I mentioned, this cognitive speech processing, even though this nomenclature people might not have used, however, for several decades, research community working in the area of brain, auditory cortex, they were very excited to know more about how the message formulation, generation, comprehension happens in human brain. In that regard, they were putting forward many studies, and but now, even though at that point of time, conventional speech processing community, we did not pay attention to that, but now the time has come. Since we have large computing power and also many of these conventional speech processing tasks where the performance has reached human level performance, now we can take up many more challenging tasks for automatic processing, but we are very effortless for cognitive systems. That is where venturing into this cognitive speech processing area will benefit many of us. Accordingly, I am assuming that many of you will take up leadership in this direction by submitting a proposal to DST. And of course, my association with Professor Rufinar goes back to 7-8 years. Initially, we had one Indo-Argentina project, a joint project with him. He visited IIT Guwahati twice, and then once. Then I also visited Argentina. We had joint work, joint publications. He also gave one earlier GAN course at IIT Guwahati on what is called brain-computer interface. Now, as a next follow-up of that, we planned for this cognitive speech processing area. I think his group is working very well in this area for a few years, and they have very good publications and many databases they have collected and made it public. We can benefit from his rich experience from his and his group. That is what I'm hoping for this week. All of us will come to know about this field of research, even though it's very small time to get hold on to the field. So with these brief words, I wish all the best for your participant. But now let me request Dr. Bharat, head of the Department of Electrical Engineering, to say a few words about the department. Dr. Bharat.
Yeah, thanks, Professor Prasanna. Can I share the screen? I have a
Yes, please. I have stopped sharing.
Can you see the screen?
And not it. I think it's coming up. Now it has come, Bharat.
Okay, let me start. Good afternoon, everyone, and welcome to this GAN course. First of all, I would like to thank Professor Prasanna and his team for organizing such a wonderful workshop. So if you look at the topic and the details, you can clearly see that there are a lot of potential applications. Based on the course, I am sure you will, many of you will be excited to work in this field, and I hope some of you will take up this field seriously and pursue a career in this. So I'll take this some time off to introduce you to electrical engineering at IIT Dharwad. So myself, Bharat, I'm the head of the department. So basically what we focus on is, building of physical devices by looking at both practical as well as theoretical aspects of physical systems related to electrical engineering. That means we focus on both. Currently, we have around 15 faculty, 1 professor and 14 assistant professors working in the broad areas of, power systems, power electronics, which is the core electrical engineering, to wireless communications, IoT, to some areas of computer science as well, such as ML and deep neural networks, etc. So essentially, we work in a interdisciplinary sort of areas as well. So there are a lot of projects that we have undertaken, which is multidisciplinary. So here are a few examples. For example, agri-tech with chemistry, cancer detection with biology, and so on. So we have BTech program, MS by research, PhD, and recently we have we are starting MTech in DSAI, that is data science and artificial intelligence, and also on smart mobility. So we have innovated in different ways to give flexibilities to students. For example, introducing half semester wherein which introduces students to some broad areas of electrical engineering. If they are interested, they can pursue further by taking electives. In terms of student research labs and achievements, we have around 50 plus journals and conferences in refereed or top-notch journals and conferences. And we have a project of 5+ crores and many consultancy projects. So many of our students have won national and awards in national competitions. And also a lot of our students get admitted to top schools for their graduate studies around the world. So I'll complete my presentation by basically an advertisement. So we are looking for bright students for MS, PhD and MTech programs. So if any of you are interested, or if you know someone who is interested in pursuing further studies, so please advertise this. Please send this information across. With this, I wish you all the best. I'm sure you will enjoy the GAN course. Thank you.
Thank you, Bharat. Thank you very much. Maybe you may stop sharing the screen.
Yeah.
Thank you. Now I request Professor Sheshu, Director of IIT Dharwad, to address the participants. Please, sir. Please unmute your mic, sir. Sorry.
Yeah. Thanks, Prasanna. Good afternoon to all those from India, and very good morning to Professor Rufiner. I think it's not even 7 a.m. For you, I think, for you in Argentina. It's probably 6:30.
Even early.
Okay. Yeah, thank you so much for kindly agreeing to co-host this GYAN course with Professor Prasanna. And it's a very inconvenient time for you, I understand. And thanks for accommodating this odd time at 6:30 in the morning. So welcome to all of the participants on behalf of the organizers of this course, Professor Prasanna and Professor Rufiner and their teams. And I'm sure you are looking forward to exciting course modules on various topics associated with speech processing. Usually a course on speech processing renders me speechless. But this course, Prasanna put me right up front and said, you have to speak about the institute and welcome the participants and so on and so forth. So it's very interesting for me to see that there are participants from all over the country. I was just going through the list. There are participants from the very northeast, maybe Nagaland, Manipur, and so on. The North India, Himachal Pradesh, and so on, I could see. The western side, Mumbai and adjoining areas. Down south, Trichy, I could see a few participants. So we have actually a large number of participants coming from all various corners of the country. And for Professor Rufiner's benefit, you may probably be surprised to know that all of them don't speak the same mother tongue. So they would actually be speaking in their own different languages. It would have been actually wonderful to have you all here in person and listen to you all speak in your own mother tongues and let the algorithms developed by Professor Rufiner and Professor Prasanna and teams do the translations and have fun. But due to the continuing situation with pandemic, we are doing it online. Maybe we will soon be able to come out of this and host you all in person. A special invite to Professor Rufiner and team. Please do make it a point to visit us. This is now approaching summertime for us, and the highest temperature is perhaps today. I parked my car outside in the sun during lunch break, and it showed me 37 degrees as the temperature. So about 99 degree Fahrenheit, for those of you who are familiar with Fahrenheit. So that is probably as hot as it gets in the summer. Rest of the year, it is even more pleasant here. Very green place. Dharwad is at the foothills of the Western Ghats. Receives copious amount of rain. It's extremely green. A very nice place to stay. And Prasanna is supposed to be one of the best hosts in this part of the country. So he will take care of all of you very well when you visit him here. About the institute itself, we are now a group of 23 IITs, Indian Institutes of Technology, as some of you are familiar with. We are probably the youngest of all these 23 IITs. We started in 2016. We graduated 2 batches of students, undergraduate students. But I should proudly say that we have achieved about 80 to 85% graduation placements or higher education admissions, which is extremely good for a new institution graduating its first and second batches. This year, in fact, we will be graduating our 3rd batch. I am also very happy to announce that we have awarded the very first doctoral degree of the institute in the very first convocation itself. Our faculty members have been working tirelessly to bring lots of projects to the institute. Across all the departments, we have about now 60 faculty members. I think we have about 1.5 project per person, about 80 to 90 projects are ongoing, which is a healthy trend for a new institution. In terms of rupees, it is about 20 crores worth of sponsored research projects, which means that the funding agencies actually trust the faculty members to deliver on the project proposals, which is a very healthy sign again. Also importantly, we have executed and we are executing lots of industrial consultancy projects. And I am also happy to say that many industries have invested in us through their donations. Recently, we have launched a Center of Excellence in Energy with substantial funding from Honeywell. We have also launched a space data science lab with the sponsorship from another corporation called Antariksh, which is the commercial arm of our Indian Space Research Organization. Through them, we expect to have access to a lot of satellite imagery data. We are also stitching partnerships with other such industries and corporates to get more involvement between the industry and academia, because that is very important for an academic institution. Some time ago, I think late last year or so, Prasanna would know the exact date, we have conducted another workshop in speech processing using, I think, Ekstep Foundation, which was also very well attended. I think we had about 150 or so participants from all over India. It was extremely popular. There a lot of hands-on exercises were conducted, a lot of algorithms, programs were taught and developed for variety of applications in their own mother tongues, because again, we had participants from several states of India, each with their mother tongues. So it was very interesting exercise at that time, and we had our famous IIT alumnus, Nandan Nilekani as the chief guest at the valedictory function, who was very much appreciating the work done by this group in speech processing. In terms of the course contents itself, I am sure Professor Prasanna would detail more, but speech processing and data analytics, AI, ML algorithms related to that require a tremendous amount of computing power. And as a new institute, you may wonder if we have the necessary infrastructure for that. I am happy to say that we have one of the best high performance computing facilities in this region. We have both CPU based supercomputing facilities and a GPU based supercomputing facilities. We have a massive visualization wall erected here in our data science lab. So it would promote a lot of activities related to data analytics, which will also help the speech processing and machine learning community. Of course, one other application area we are seeing for all this data analytics and machine learning is related to climate and environmental impact. As some of you from India would probably know, Karnataka is the second most arid state in our country. So one of the issues we have taken up as another focus is to look at water related issues. we are at the foothills of Western Ghats. So it is important for our institute to look at the applications related to water and climate impact. So those of you who are interested in looking at high performance computing applications in these areas, not just speech processing and so on, would find resonance with some of our faculty members from electrical engineering, from mechanical engineering, from computer science and engineering and so on, or even physics for that matter, mathematics and so on. So please do take an opportunity to visit the institute, interact with the faculty members. If you are not able to visit also, do drop an email because most of the details are available on our website. Those of the participants who are interested in taking this initiative forward in any area of interest to them, please do feel free to approach the concerned faculty member and then take the collaboration forward from whichever institute you may be. Okay. I wish the course all the very best. Have a wonderful time. Good luck.
Thank you very much, sir, for that brief and detailed information about the institute. Now I'll request Professor Bapat, Dean Academic Programs at IIT Dharwad, to say a few words about it. Thank you.
Thank you, Professor Prasanna. Welcome to Professor Rupinath, the expert in the area as such from abroad, Argentina to be specific, and Jagbandhu Mishra, Ayush Agrawal as the other co-speakers in the program as such. Welcome to you all. Very good morning to Professor Rupinath, whereas I have to say good afternoon to our people in India as such. It's nice thing. It's really encouraging to see that you could spare time in the early morning and be here for this particular inauguration program as well. The speech processing, as we know, as uneducated persons in that area, we only look at it as one way of communicating as such. But there are so many other things linked with the speech processing. We are aware about the automatic machine translation and things of that kind, but that can reach only a particular level and everything needs certain background. That background information is generally not there for most of us. We know the final effect at times, but we don't know really how it is done, why it is done, in what fashion it can be improvised. These ideas we don't have. The course content, as has been mentioned, like the human-computer interface or the brain-computer interface, these are all going to be finally linked with the computer interfaces as such in general. And as Professor Seshu has pointed out, we need a high-speed computer for all such applications in general as such. I expect it will not be any different for the cognitive speech processing program as well. That also will be needing all these things. I went to the details about the various topics and other aspects as such, and I realized that the lectures and tutorials are hands-on. There is almost equal importance given to the hands-on part as well as the tutorials, and that is something which really helps a new person who is stepping into this arena as such for the first time. It will be really good to see that about 10 tutorials or hands-on sessions will be there for these people. Of course, Professor Prasanna has been working on this area and as he explained in the beginning, has been in contact with you, working together. So things will be moving very smoothly and nicely. I am sure about that part as such. The Department of Electrical Engineering is also happy to support such activities as such, and so is the institute. Being the Dean Academic Program, certainly it gives me a pleasure to have certain activities under this GAN program, which is effective from 2015 or so, 5-6 years back. It was initiated and it's taking good shape, and quite a few programs are running under that, utilizing the expertise of the foreign experts as such. Like Professor Rupinath, will be very happy to have you around, and as Professor Seshu said, it will be nice if you can visit in person the institute it will be nice to receive you at this end as such. To all the participants who are there in the program, I suggest that you make the most of it. Such opportunities don't come time and again. Having Professor Rupina around, as well as the other professors and Professor Prasanna, all are so nicely putting it to you. Grab it with both hands as such. These opportunities really won't be there time and again. So wish you all a very best short program of 5 days. But I'm sure you will not remember it for at least 5 years, but maybe 5 decades as such. All the best to you all. Thank you.
Thank you very much, sir, for those kind words. May I request Professor Rufiner to mention few words about this cognitive speech processing. Anyway, we will have your lecture immediately after this. I'll request you to address the participant, Professor Rufiner. Please unmute your mic.
Okay. Thank you very much for invitation for this course. I'm really very happy. As Professor Prasanna told you, we are planning this course since, I think, 2019, but then COVID pandemics go around all the world, and we have to suspend our plans. But now we have the opportunity to give it online. I visit India 3 times. It's a beautiful country. Professor Jesus, thank you for your invitation. I am really very interested to go again there. Go to Dharwad also and visit the campus in 2018 when you are just beginning, I think, with all the facilities there. And I am really very happy. It's a pleasure for me to stay with all of you here, giving these talks and sharing some of my experience in these topics during the last years. We are working with Professor Prasanna. We collaborate for many years, I think. He also visited Argentina and my lab in the past. So this course, I think that is the fruit of the many years of collaborations. So now I work at the Research Institute for Signal System and Computational Intelligence. I don't know if you want a very, very small presentation of my group, Professor Prasanna.
Please, you can first.
So I will share my screen.
Yeah, please. Yeah, it's visible.
Well, yes. A very, very little presentation about my group. Here we are almost 20 researchers in different areas. We have some doctoral and postdoctoral students and graduate students. The total group of people is around 50 people working in different areas of the computational intelligence and signal processing in general and systems. So the main research areas of the Institute are computational intelligence, signal and image processing, and also complex systems. There are many techniques we are working from different application areas. In computational intelligence, we can mention deep learning, data mining, bioinspired heuristics, and so on. In signal processing, sparse representation that is important also in this course. Statistical and bioinspired signal processing, and so on. And in complex systems, we have also evolutionary multi-agent systems, adaptive control, robotics, etc. we have a application in many fields like the medicine, bioinformatics, man-machine interface, agriculture, and others. And for example, the group is working in pathology detection, especially in cardiac and sleep apneas. We have several publications, but also patents here in this area. We also work with enterprises in order to transfer the knowledge from academy to the industry. We also work in human-machine interfaces, speech recognition, signal recognition, brain-computer interfaces. This is particular my area of work. We also work in agriculture, different applications in detect how the animals feed, only taking the sound signal from the animal when it's taking the feed. We have also patents in this area, and there's part of the group that is working in robotics, autonomous vehicles, navigation, and all of that, and even in the modeling of epidemics like COVID-19. We developed a very huge model for the pandemics here with an ancient-based model that was very useful during this time. We also work in computer vision with several applications in several areas in medicine and agriculture, precision agriculture, and also robotics. In bioinformatics, we have several algorithms and even patents here. All the works are very interdisciplinary, working with teams for other areas of specialization. Here, biologists, but we also work with physicians and engineers for other disciplines. So this is only a very, very brief introduction to my group. Now, since the past year, I am the head of the institute also. So I have to share my academic activities with some administration activities. So I understand that this is part of the work. And well, nothing more for this. I want to thank Professor Seshu, Bapat, and the rest of the authorities, and especially Professor Prasanna and his group for its support in this course. Thank you very much.
Thank you, Professor Rufina. So let me thank Professor Seshu, Professor Bapat, Professor Amar, and Professor Bharat for participating in this inaugural event. So this is, at least I am looking forward for knowing more about this field. I request all the participants to take maximum benefit of this, as Professor Bapat mentioned. Even though you are not working in the area, at least it is good to get a feel for what is happening in this field. And also this hands-on session, the group members from our group and Professor Rufina group are working for last 2-3 weeks to come up with the programs, run the programs, and ready for demonstration to all of you, and also hand it over the information. So please participate and take benefit of this. All the best for your course. Thank you all. So thank you, sir. Thank you, Seshu sir. Thank you.
Thank you so much.
Thank you.
Rupna.
Yeah, I request Professor Rufina to start his first lecture.
Okay. Bye.
Bye.
Thank you.
Thank you.
Well, thank you. I will share my screen again.
Yes, please.
Well, Professor Prasanna gave us a very huge and broad idea of what is cognitive speech processing. In what follows, I will try to introduce the course or the lectures that we'll have to pass through, and the principal ideas, the main focus of this very, very new area of cognitive speech processing. So I began to present the course outline. So the main objective of our course is to presenting human speech generation and perception with an emphasis in cognitive speech processing. Then we want to explain the different techniques in speech and all the related biosignal processing, including the last recent techniques in the field of artificial intelligence, neural networks, and deep learning. We want to discuss all speech-related issues with brain-computer interfaces. In the last years, many researchers from brain-computer interfaces pay attention to the potential of speech-related signals in order to get more robust and more fast interfaces with machines. So we discussed the last works in these directions. We also want to analyze and use different biosignals, open databases. You know that one of the main issues when you want to process and try to recognize the signals is to have big databases in order to adjust and train the artificial intelligence tools in order to get the things work. So we present the main open access databases, including some databases that we recorded in our group. And of course, the idea is also to have some tutorials, hand-on tutorials on speech-related biosignals, processing methods, and all the applications. Here we try to put you in contact with the signals in order that you can manipulate them, extract useful information, especially from brain signals, trying to extract information about the speech production and speech perception process. And finally, we want to present and discuss together which are the new directions and challenges for cognitive speech processing. So these are the main objectives of our course. I now go day by day trying to introduce the main aspects of each lecture. Well, we are in the day one today. Professor Prasanna gave us a broad introduction but to his cognitive speech processing. Sorry. Now in this lecture, I try to give a brief overview of the course and an introduction of the main topics we will see in the next days. And then after this, we have the first tutorial. It's an overview of MATLAB and Python and some basic DSP tools in order to put hands-on all this stuff. And then tomorrow, day 2, Professor Prasanna will introduce us in human speech production, perception, and cognition. This really is a field that advanced a lot in the last years because of the broad technologies that we have, imaging technologies, for example, and the amount of data processing we have now, computers and all of that, permit to deep insights in what the human speech production, perception, and condition process was really. Here, the research in this field is really, I think, from the last 50 years. But in the last 10 years, we have a very, very impressive advance because of all these tools. After this, tomorrow also, I will give you the basics of brain-computer interfaces. We will see which type of works we do with this type of interfaces. The idea here is to not only help people with disabilities that they haven't any other way to communicate with us and with computers, but also to try to mimic some of the characteristics of the human communication in order to get better human-computer interfaces. So we will see or review the basic techniques behind this, the paradigms, the signals, the equipment, all of this stuff. We will try to see tomorrow in the lecture. And then in the tutorial, the idea is that you can get and work and play with some EEG signals, and also to make some basic processing and pre-processing of the signal in order to remove artifacts and filter the signal. That's the idea for tomorrow. Then on day 3, on Wednesday, Professor Prasanna will introduce the fundamentals aspect of automatic speech recognition. He is working in these fields from many years, so I think he can give a brief overview of the field in 1 hour. It's a little time for all the things that we know about this issue, but the focus in this course is more in brain signals, brain-related speech signals. So then, after that lecture, I will introduce intelligent ambient disparate acoustic automatic speech recognition and processing. In this talk, I will try to show you how bioinspiration can help our research in order to get or to mimic some of the sensorial characteristics of human speech processing. So I work in this area, and I have some published papers in this issue. So I try to share with you or the main ideas behind this topic. And then in lecture 7, we try to present the main speech-related biosignals. I think that the classic approach of computer and automatic speech recognition is to work with acoustic signal. But if you pay attention to the whole speech production process, you can see that we can measure many different signals. Perhaps some examples are electroglottogram or electromyogram, or even EEG or other brain signals. So in the last years, some researchers began to try to find important information in these other signals different from acoustic one. So in this lecture, we will have an overview of this stuff. And in the tutorial for that day, we work with the speech-related signals, especially EEG. The idea here is to try to extract some important information about speech from the EEG signal. For example, the energy envelope of the signal and there are other low frequency signals that are easily can be easily extract or relatively easily extract from EEG signal. So that's the main topic of this tutorial. Then on day 4, Professor Prasanna gave us an introduction to artificial intelligence, especially by inspired methods, neural networks, and deep learning. We know that deep learning was introduced not many years ago, and with very, very impressive results, because with this type of focus or this type of techniques, you can really beat most of benchmarks in many, many applications, inclusive in computer and automatic speech recognition. So which characteristics make this type of technique successful? Well, Professor Prasanna will introduce us. Then in lecture 9, I will introduce different aspects of relation of speech with BCI, brain computer interfaces. Here, the idea is try to understand the main aspects involving the production and perception of speech, and how we can use this type of information and signals in order to better communicate with computers or other persons. And in the tutorial session, we will put hands-on some computational intelligence and deep learning application, especially in this field. We work with some EEG databases and try to reproduce the results of, for example, words classification, isolated words classification from EEG. This perhaps the idea is to work with one of our published databases, open access. In the last day, we will see in the first part, lecture 10, for Professor Prasanna. He will review the main speech processing technologies. Then I will introduce and we talk about one paradigm that called imagined speech or inner speech. Really, there are different terminology used by different researchers. So we will try to clarify the difference between silent speech, imagined speech, inner speech, and other speech-related paradigms in brain-computer interfaces. Then we will review the main biosignal databases, especially open access ones, because the idea is that you have a broad idea of the different data that is available to work with for this type of applications. Then we will discuss all together about the applications, recent applications and new directions in cognitive speech processing. The idea here is to, I will share with all of you some important, the main papers for this field in the last years. So we have to read them carefully, and then we make a discussion all together about the main direction in the future of this field. In the tutorial session, we will work with some open access databases, especially one inner speech database that we have just published this year. I think last week the paper was published. So we will share with you all the data, and you have the opportunity to process it and even make some simple classification between modalities or even between words recognition. So with this, we've finished the tutorials and the lectures, and then the idea is to have a brief examination and multiple choice in order to get some feedback about what all this stuff is useful for you. So this is a brief overview of all the lectures and the activities of the course. Only a brief acceleration about the discussion. The idea here is that we will randomly assign one particular paper number for each participant. I am thinking in 10 papers. I see that we have more or less 30 students. Perhaps I will add a little 1 or 2 papers more. The idea is that we will send all the papers to all the participants, all the students. You must read during these days your assigned paper in depth and carefully. Then you should discuss main ideas about it with other participants also during these days. You can also read some of the other papers. This is optional if you want, if you have time, and if you want to know more about the field. And then in the last day, lecture 12, altogether we will use all the material in order to discuss about these new challenges and opportunities in cognitive speech processing. This is the idea. I don't know if something have some question. I can answer some question if you have from this general overview.
Any of you have any clarifications or questions? Any of you? Yeah. Anyway, then Professor Ruffiner, we can proceed.
Okay. Well, now we will see an introduction for this cognitive speech processing. Well, one of the main focus of this type of field, this new field, is on human-computer interfaces. You know that human-computer interfaces are really nowadays everywhere. Now in this talk, I am using mouse and keyboard, and also we have now tablets and or other interfaces. We can also talk to our computers with very good results. I think that in some of these applications, 10 or 15 years ago, we thought that it was very difficult to make the progress that we done in the last 5-6 years, I think. But there are some signals that are even hard to process and to extract information that are brain signals. I think that from all the bio-generated signals, perhaps brain signals are the most complex ones. Our comprehension about the brain is still incomplete. So the idea here is to use our voice, but not only the acoustic signal, as already mentioned. You know that the voice and the speech signal is one of the most natural forms of communication between humans. It's also one of the most studied biosignals, with several years of research to create human-computer interfaces. We can think about this signal, speech signal. It really conveys information from different aspects of the speaker. For example, emotional state. In the picture, you can see a person that perhaps is angry, and he's shouting to the telephone, I think. All that emotional state you can infer from a speech signal, from the acoustic speech signal. Also health. If you have some laryngeal pathology and your phonation is not normal, you can infer that or extract information about the pathology or the affection to the, for example, for the vocal cords from the speech signal also. Even you can use this signal as a biometric signal in order to identify the person who is talking. So this was used in the past for authentication and security, the process to access a computer, for example, or even our cell phones. You can also extract some information about age. This is not perfect, but if you have the recording of the speech signal, you can say more or less which is the age of the speaker. That's very, very interesting also. And even sex and even height. You can also know because of the how long is the vocal tract impact in some characteristics of the speech signal. So you can almost know more or less how many centimeters the person or the speaker have. And many others. I think that we can together try to think in other information that we can extract from this only signal, only from the acoustic signal. But sometimes there's problems with producing the signal. The people have some disability, so they can't talk, or you are in a very acoustic contaminated environment, so you can take complementary information from other speech-related signals. That the idea. So it is the question for us now is that it is possible to use biosignals related to the speech production process, but different from the acoustic signal. I was already mentioned some advantages. The complementary discriminant information is one of them, because it's the same process, for example, the speech production process, but you have many signals in order to get information from this process. Acoustic one is a classic approach, but we have another signals that we can register and analyze and take information from there. We can make some applications that are noise robust, that have noise robustness characteristics, because, for example, if you are in a plane with a lot of noise, background noise from engines and all of that, acoustic signal is very contaminated. So if you use, for example, EMG, you can take some information in order to better recognize the speech of the pilot. Also, privacy is an important issue here, because sometimes if you try to use silent communication modes, you preserve the speech or the message from other person to know what you are talking about. And finally, you can help people with oral communication difficulties, as I already mentioned, people laryngotomized or with some disability in their language. Well, you can use other signals, because some people, they can't even produce any sound, but some of the anatomical organs are there, and you can use information during trying to produce a speech in order to trying to detect or recognize what the person is saying or trying to say. So these are some advantages of trying to process speech-related signals. But human oral communication is really a very, very complex physiological process, because it involves the interaction and coordination of different parts, organs of the body that produce many, many signals, as we saw now, that can be measured and analyzed. So in the recent years, several researchers have attempted to better understand the entire process. This process has been studied for many, many years. But as I told you, it's in the recent years when the different imaging techniques and the different ways to get a new type of signals and information from that signals that permits us to trying to better understand the entire process of human speech generation and perception, especially from brain signals. That is the most challenging problem. So this leads to, as we already told, to the new field of cognitive speech processing, as also Professor Prasanna presented us. So let us see some examples of signals that we can use for this cognitive speech processing, oral signal related to speech production or perception even, but most of the focus is in the speech production. All the signals derived from muscular activity are important in EMG. When you talk, like I am talking now, several muscles are activated in coordination. So if you put electrodes in several parts of the head, you can register the evolution of these signals, and you can use it in order to try to recognize speech. There are some methods, all techniques.
Professor
Like,
Rupina,
yes,
I have a question.
yes.
So how do we include this EMG or EGG as a part of cognitive processing?
No, here really this is more speech-related signals other than acoustic.
Okay.
Cognitive speech processing is focusing in brain signals also only,
Okay. Okay.
or principal. But these other signals can give us some insights of all the communication or the speech production process.
Okay. Okay.
So it is important to have all the picture here of which other signals different from acoustic appears when you try to study the speech production system.
Okay.
But then we focus especially in brain signals.
Okay. Okay. So when we come to this EMG activity, muscle activity, how much efficient it will be in terms of coding information related to?
Well, not all the characteristics of a speech are there. For example, phonation, the laryngeal cord activity, you don't see in EMG because it's only surface EMG. You have to put some electrodes inside the throat and it's invasive. But from EMG, you can infer some characteristic of speech, not complete speech recognition like with acoustic signal, but you have many information there because all articulation information of speech you can get there, or the principal information you can get there. So, for example, if you have to control some wheelchair, you can use only basic words like left, right, front, directions. And in this context, you can use EMG in order to recognize from small vocabulary words. You are mute.
Yes, I got it.
Okay. Well, a signal that it was used during a lot of time is EGG, electroglottogram. I think that your group, Professor Prasanna, work a lot with this type of
EGG signal wave work.
The idea here is that we have to sort that all these signals are related and also related with brain signals, because the brain is the part of the body which coordinate all of the speech production process. So there are some relation and coordination between all these signals. Another signal or another study that can give us information about speech production is electropalatography. Then we will review some other issues and details of every one of these techniques. The idea here is only have a broad picture of all the signals. Electropalatography was used to diagnostic some speech pathologies in the past and try to understand also the speech production process. Another technique, a little less known, is electromagnetic articulography, that use some electrodes in the tongue and an electromagnetic coil in order to get some signals about the motion of the tongue and other articulators in mouth. inside the mouth. And of course, different imaging and video techniques, like the common video recordings or ultrasound recordings or tomography videos and all of that. All this stuff gives us information about the speech production process. And of course, all the brain-related activity signals. Here we have many ways to record signals related to brain activity. I only mentioned some of them. Electroencephalography, that is one of the most used for many reasons. We will see which are the reasons for its broad use. Electrocorticography, FNIRS, magnetoencephalography, etc. Many types of studies that can get information and signal from brain-related activities, especially related to speech. And the later signals are especially interesting because they are also used for brain-computer interfaces. So here you have a point of touch between both fields, all speech processing and brain-computer interface, and especially in the common field of cognitive speech processing. So you have, as I already mentioned, several signals for register brain activity. Electrocorticography is a technique where you put some electrodes inside the brain. So this is an invasive technique. Another invasive technique are intracranial electroencephalography. Also, you have some brain surface electrode there, put inside your head, touching the cortex, the brain cortex. These types of studies are very important in order to understand how the signals are processed in the brain, especially speech-related signals, but are very invasive, and there is no possibility that, for now, I think, that this type of techniques will be used broadly. I think that perhaps in the near future, or have some electrodes implanted in our heads, but now this is really hard and have many problems. Another important source of information from the brain process is magnetoencephalography. Here the equipment is very big and it is not portable, and it's interesting also for research, but not for everyday use. So for brain-computer interface, it's a little difficult to work with this type of technologies. Functional magnetic resonance imaging is also there. It is not portable, and all these equipment are very expensive too. So again, they are not useful for everyday activities. Functional near-infrared spectrography, or FNIRS, is recently appeared technique, relatively recently, with low cost and portable possibility. So this is, I think, an interesting alternative for registering and recording brain signals for brain-computer interfaces, low-cost brain-computer interfaces. And of course, electroencephalography, that is one of the most used signals from brain activities. The advantages of electroencephalography is a standard technique, one of the first developed techniques for studying the brain, some like 100 years of age. It is not invasive. Well, some more or less. You see the picture at the left with the person with so much electrode there, you can even move. But we can see, we can talk about a non-invasive technique. It's accessible, low cost, relatively low cost. We have $1,000 equipment with good characteristics to register this EEG signal. The equipment are portable. Even you have also some wireless equipment, so you can put the cap and it's all wireless, the communication with the computer. And it have a good compromise of the temporal spatial resolution. So it is possible to get or extract important information from each signal. So most of the open access databases work with EEG, and particularly the two open access databases that we develop in our group are based on EEG recordings. But what really happens in the brain during spoken speech? This is a very, very difficult question. In the first years, we have very oversimplified models of the process of producing speech. In the last years, neuroscientists work very hard in order to get better speech production models. During the course, we will review some of them. I have to say that still now there isn't a common accepted more speech production model for the neuroscientists. But we discuss main difference and take an idea of what happens there in the brain during speech, and which are the main areas or where to look. Because when you have all the brain signals, for example, EEG there, you have many signals from different channels, and each channel is in different parts of the brain cortex. So you have to have some cues in order to where to look the useful information. This is not easy, and it even is a point of research, on very active research now. But we will discuss some of the speech production models and how to orient them in order to look the important information for a speech classification, for example. And also we can ask, what's about the words and the brain when you use the words in different contexts? Because when you producing the words, some mechanisms arrives and you have some signals in some parts, some locations of the brain. But it's different to see the word or read the word. For example, you have a verb. I don't know, any verb or word. For example, to talk. You can read the words to talk or talk. And when you see the word write in a paper, for example, one specifically area of the brain cortex activated, that is the the visual cortex in the back of the brain. Here in the picture is the upper left picture. Here we can see in red colors the highest activity of the brain. But then when you, for example, hear the same word, to talk or talk, when you hear the word pronounced by another person, then auditory cortex activates in a very complex patterns. Here you have only one instant photograph. All these images are generated by positron emission tomography that detects blood flow in the brain. So where you have high activity, you have also high blood flow. So you can make this. And here in the lower right, you can see what happens when, sorry, lower left here, when you speak, when you pronounce the word, then some portion here of what it is the Broca area, and some of the motor cortex also is activated. And then when you think about verbs like talk, many regions of the brain are activated altogether. Well, this is only an idea of what happens inside the brain, because it isn't only the word, but the context and the modality you use that word, how the brain process the word or the concept or the meaning or the speech production or the sound, etc. Well, this type of analysis can permit us to make really amazing things, like speak what you are thinking. You are thinking now one ideas is what we will call in speech or imagine speech. You only imagine what you are thinking like now. If during this talk I really have a voice inside my head, my inner voice that is telling me what to say, but you can really get access to this inner voice with some of these brain-related signals, and that make possible it's a difficult problem, but you can speak what you think. This is the task: speak what you think. So here, for example, we have some electrodes inside the brain, and you can register simultaneously here the EEG signals, or some information derived from EEG signals, and also simultaneously the speech. This is called over speech, and you can try to see which information is there from speech in EEG signals or related signals. So you can pronounce some words here. This is the pronounce mode, or even only think in the words, like here, hungry, thirsty. And you have also some register from electrocardiography here, corticography here, but no acoustic signal. And you try to recognize inner speech or imaginability of the signals. This problem is more or less hard. This picture is from electrodes implanted inside the brain, and signal to noise ratio is very high, and the quality of signals is high also. So it is more easy to recognize inner speech from this type of recordings. Another possibility is also to hear what you hear. If you put some electrodes in the auditory cortex, you can also register the signals there, and with some models, linear and nonlinear models, you can synthesize or reconstruct, for example, the spectrogram or even the speech signal you are hearing. So this is amazing too. I think that is very interesting. This work is from 2012. As I already mentioned many years ago, this is like science fiction, I think, because really a few years ago we began to think about solve this type of problems. We even in this respect, even with EEG signals, because these type of studies are also with implanted electrodes inside the brain, but even with EEG signals, now you can extract very basic information about speech, like the envelope or the intonation, F0, for example, or other speech-related information you can extract now from EEG. And in one of the tutorials, we try to reproduce these results. Here in this picture, you can see the EEG in black, and here superimposed in red is the speech envelope. And with the linear model, you can use, this is only one channel of EEG, you have many channels. And the transformation here that you will use is first one to multidimensional map, and then that's the direct model, and then an inverse model is to multiple dimensions, EEG, for example, or in this case, to one-dimensional speech envelope or speech intonation. So with this type of models, multidimensional regression models, almost linear, or the main works with linear models. You can reconstruct very well this type of basic speech information. So we try to do this with the EEG from a person that is hearing the voice from another person. But even if you are talking like me, when I am talking, I am hearing what I am saying. So it is possible to also use my EEG in the auditory cortex in order to hear or see what I am hearing about my own voice. So this type of things we can do with these signals. Well, and arriving to brain-computer interfaces, well, brain-computer interface users with control channels that are independent of the brain's normal output channels, like the peripheral nervous system and muscles. You use only signals inside the brain or register from inside the brain or from the brain. And the idea is that with that signals, you can control some devices or the computer, or even to try to communicate with other people. So the main blocks of a brain-computer interface are a system for signal acquisition, some of the equipment that we have just mentioned, like EEG or electrocorticography or some of that, or FNIRS, some of that, record brain signals. Then you have a signal processing and classification stage. You make there some basic pre-processing, like artifact removal and a conditionation of the signals, like EEG or ECOG or something like that. Then you have, in the classic approach, a feature extraction stage. And so you can get the main characteristics of cues in order to classify the different signals from the brain. Then usually you have a feature selection, because here you have many features. You can see that you have hundreds of channels there with temporal information in each one of the channels. So generally you have plenty of features or characteristics that you can extract. So the feature selection stage is for only select the characteristic with information related with the classification task. And then the classic approach have a classification stage. Here you can put any classification technique, like neural networks or pattern classification or recognition techniques. And at the output of this stage, you have another stage that it calls the translation stage, because here, the output of the classification, you have the class of the signals registered. For example, one phoneme or one word. And then the idea is to translate.
Professor Rufina,
Yes,
I have a doubt here.
yes.
Once we acquire that EEG signal, it is mostly one-dimensional, no?
No,
In two-dimensional, this is, how do you get this spectrotemporal patterns like thing what you have, feature generation?
yes. Brain signals in general have are multidimensional. You have, for example, electrodes in different parts of the skull. So you register, for example, 128 signals there, temporal signals.
Okay.
Spectrotemporal receptive fields or something related with the processing of the signals in the brain are generally related with specific neurons. All these techniques register the activity for many neurons for each channel. Or each channel is not the activity of only one neuron, but thousands of neurons for each channel. But neurons that are in a particular area of the brain cortex. And you need, because different processing of speech signals are located in different parts of the brain. So you need altogether simultaneously recording of the activity of the brain in all those areas or locations in the skull. It's okay?
So then the in that feature generation block, no, the images that you have shown, those are spectrograms or what?
That's only like example. You can make some spectrotemporal representation of each channel here. But this is very high dimensional because this is high dimensional for one channel. And imagine if you put hundreds of channels there, you have a huge amount of characteristics. And it is difficult to process with many of the actual techniques, I think. So the idea here is to one type of reduction dimensional technique or feature selection in order to only get the most important information there. That's the idea for the traditional approach. But with deep learning, you know that all these stage comes together, and you can even work with raw data from EEG, trying to in one stage, but with many layers. You can, for example, classify the different words or different material that you have in the EEG signal, for example.
Okay.
When you have just classify the signals, you have to usually translate that class in order to some type of action, direct action, for example, to control a wheelchair or the computer or something like that. So we have here this translation stage. And this goes to some specific application to control the wheelchair or control the computer or another type of application, games or entertainment or something like that. So this is a generic BCI block diagram. Each of the stages here have its own challenge in order to extract all this information in this huge amount of information. And as I already told you, it is difficult to know where to look for which in all these signals, which are the main important or the main characteristics to extract in order to get some insight of for example, the speech production process. That's the main, I think, issue here. How to extract the information. Hopefully, we have now very, very powerful techniques like deep learning that this paradigm changed the way we work with complex signals in many fields, not only here. But
Thank you.
Thank you, Professor Prasanna. But specifically, which is a phenomena that you can use or we can use in order to control the brain-computer interface is different from one paradigm to another paradigm. The paradigms in the terminology of brain control, brain communication interfaces are the control signals that you can use in order to control the device. So you can use, for example, is what it called slow cortical potentials. You can also use steady-state visual or even auditory evoked potentials. So, for example, you can generate one stimulus, acoustic or visual, and this produce some type of evoked potentials in the cortex. So you can measure this potential, and then you can relate the potential with the stimulus, and this is and that at a particular time elapsed, about 300 milliseconds after the stimulus. There is a very specific potential there that you can measure and use in order to control the brain-computer interface. Also, motor imagery here associated with even related desynchronization or synchronization phenomena inside the brain. You can use, for example, you can imagine that you open your right or left hand, not really make the movement, but that you are making the movement, and you can use this to control some device, some wheelchair to go to right or left. If you think or imagine open the right hand, you can go right, and if you imagine to open the left hand, you can go with the wheelchair, for example, for the left. And you can use this information in order to control the device also. And finally, the main focus of this course is all the speech-related paradigms, or all the speech-related signals that we can use them in order to control different devices. This is the main issue of that we'll review in this course. Which are the advantage of using speech-related signals in order to control brain-computer interface? Well, one of them is the naturalness and speed of this type of signals to control devices versus the non-natural way of communicating of the other paradigms. Because if you have to pay attention to one particular image, or you have to pay attention of one particular function of the brain in order to elicit it, some type of signals, this in general it is not natural, and sometimes you have to train in order to produce the signals. So use them in order to control some devices. So speech-related paradigms offer a very, very natural way of communicating with computers that is our own inner speech, our own machine speech. Really, we use it every time, or all time, in order to sort, in order to express our internal ideas. So it is very natural for us to use it to control the device. This is in some ways like synthetic telepathy, something like that. As I was talking some minutes ago, this is really amazing and surprisingly for us that you can use this type of signals in order to know what you are thinking about. So another advantage is that the main effort falls on the computer and not on the patient, because you can think if you use this type of caps and try to concentrate in a particular task during a lot of time, this can be tedious and boring. So a lot of effort the patient or the person have to do in order to maintain the attention on the task. But with inner speech is not the case, because you do it more naturally. And finally, we have promising results for classification of different type of sounds or speech-related signals like vowels, syllables, and whole words using EEG signals or other signals extracted from brain. during the different modalities, spoken, imagine, or inner, because you can register brain signals in every speech modality. You can talk really and register the signals, or even you can imagine only not producing any sound, or even you can produce articulation but not the sound, or different modes of producing speech or speech related signals. So with the last techniques, especially from deep learning, you can classify some of these type of speech materials. I have to say in this point that some of the nowadays research works have results only a little over chance level, because this is a very difficult task. That's I think the reason for put much effort, much research effort in trying to decodify this type of signals. But now the results are in some of these databases a little over chance level. So many research can be done here. So as I already mentioned, we can talk in the different ways. Silent speech is one. We only move the articulation, but we can't, or don't emit any sound. We can also imagine that I pronounce the word, or only imagine the words without the pronunciation part. So many works and reviews are taking this type of signals or ways to communicate with computers. We will review the main works around these technologies during this course. This is one of the main focus, I think, and the main interest of this course to make focus on this.
Professor Rufina,
Yes.
in this article that you are listing here, this biosignal based spoken communication a survey.
Yes.
This Tanya Sul's group, they are also recording EEG signals.
Yes.
Okay.
Yes, when they talk about biosignal based spoken communication, they also use EEG signals,
Okay.
or brain signals, not only EEG. And they also propose this type of classification: silent speech, imagined speech, or inner speech. Because in the community there is some confusion. For example, imagine or inner speech are used in the same way by different researchers. We will try to put some light on this issue, because as it's a new field, different researchers and works use same word for different meanings, with different meanings. So this is a good review, but there is also a review from 2021 with a focus more on brain-computer interfaces and imagined speech and inner speech. But this review is interesting because it really take a broad picture using all biosignal related communication technology.
Thank you.
Thank you.
Professor Rupner, I have just one question. So,
Yeah, please,
uh, yeah. So I also have confused in imagined speech and inner speech. Can you
Yeah.
tell some clarification on that? What is the difference between that two? Silent speech, somewhat I know that we will not speak out. We will just articulate our lips. That is silent speech. And what about the difference between imagined and inner speech?
Yes, that's a good question. We will go into details more advanced in the course, but I can say now that in imagined speech, the idea is to you imagine that you pronounce the words. So you pay attention to the motor aspect of the communication. So you imagine pronouncing the word. You imagine that you put the tongue in one position and the motion of the lips and all of that. And also you can imagine, visually imagine you pronounce the speech, the words. In inner speech, you only focus in the meanings and sometimes in an auditory internal representation of your own voice. This phenomenon of inner speech was studied in the past by psychologists and people from neuroscience, but especially by psychologists, because some people have also imagined voice inside their heads, and in some types of dementia pathology, so they hear voices other from him. So that's the pathology side of this type of phenomena. But during normal thought, many people hear inside his head his own speech, his own inner speech. That's the name inner speech. But during the last years, some researchers talk indistinguishably between imagined and inner speech. But again, it depends on what, how the person in the experiment was instructed in order to reproduce a particular pattern. For example, if you talk to the person and you say to him or to her, please pay attention to the movements you do during imagination of a speech. That's a particular way to do it. So you expect it that you have more activity in the motor cortex. But if you instruct the person in order to not pay attention to the motor aspects, or the pronunciation, but only in the auditory imagination of its own speech, then you expected more activity in the auditory cortex. Not only there, because I have to say also that it is impossible to completely isolate it, one aspect of the other aspect of a speech production or a speech perception. But you expect it that the main information is in one particular area of the brain cortex. Do you understand?
Yes, sir. But somehow it is coinciding with again the silent speech.
Maybe in the later session when we go there, we'll get an idea.
Thank you.
Okay, yes, I will go through these concepts again during the course, and we'll see some examples and all of that. Perhaps I now go on with the next slide because of
Yes,
time.
Thank you, sir.
Thank you very much. So, why this type of problem is so hard? We try to review some of the main aspects that difficult us in order to solve, for example, the classification problem. You have all these signal, for example, there for a person trying to imagine speaking in some way. And we have to classify that signals in order to know which is the message, which is the word the person is imagining. That's a problem, a very hard problem. So the first problem is that this has a high variability, intra-individual, intra-subject, or inter-individual, between subjects. We will go on this point, but the main idea is that it's very, very high variability in the signals, in the brain signals, even more variability than other biosignal like speech. Speech signal has high variability between the speakers, but brain signals are really many times more variable from individual to individual, or from the same individual at the different moments, because in the brain you have many process simultaneously doing by your brain there, not only speaking, because it is impossible to isolate only one task. So the state of the brain is different from time to time and from subject to subject. Intrinsically, nonlinear mechanisms are involved in the production of speech, especially at the brain level. You know that the brain is constructed or formed by neurons. Neurons are particularly nonlinear devices that process the input signals in a nonlinear way, and all of them are interconnected in complex way. So this is really very complex mechanism in order to try to decode how this works. Also, there is a lot of noise there of diverse nature and intensity because of all other processes that we are doing in our brain. For example, our brain is taking attention to not only in the process of producing the sounds of speech, but also the brain is controlling our heart, our lungs, all other living process of all our body. So it is difficult to isolate the important signal from noise, from not only brain signal noise, but noise from all other process around you also. These signals have very complex and generally chaotic temporal dynamics. So very small changes in initial conditions or the position of the electrodes and or the state of the mind of the subject, all these can change completely the temporal evolution of the signals. From the point of view of the classification problem, classification stage, you have many classes and and generally very overlap between them in the feature space. So it has very difficult classification problems. You also higher order statistic process involved more than Gaussian process than like the classical approach. You have to use here for this type of, for example, for sparse signal processing, you have to use a higher order statistics other than Gaussian, because the activations at the neurons, for example, as Professor Prasanna told us, you have one neuron that it being activated for a particular sound between millions of neurons, but that neurons activated only very few times during speech. So that's is more better understand using probability distribution like the Laplacian probability distributions or something like that with high peaks in zero. So this, you have to use higher order statistics in order to work with this type of signals. A lot of redundancy of information between different signals. For example, if you measure signal with electrodes that are near in the brain in near positions, you have some correlation there because you are measuring the potentials in the surface in one location, and if you move only 1 centimeter, for example, to the left or to the right, you register similar signals. So there is a lot of redundancy there that you also have to use in order to get, for example, better robustness for the system. And also high dimensionality. I have already mentioned that Professor Prasanna asked me, you have many dimensions here. So this is also a problem. But I will focus now in high variability. Well, brain differs in many forms between subjects. For example, at the anatomy level, the cortex folding of every subject is different. Of course, we have some common characteristics, but when you see one brain is different with a brain from another subject. The functional map also, or the functional map is which areas of the brain are responsible for each task. For example, in speech production, but there are common characteristics. But the brain from one person, it is the functional map. It isn't exactly the same from every person, every subject. And other differences are by sex of the person, mental condition. For example, you can have a person with some mental pathology, and that's also produce different activations in the cortex, or even between normal persons, you have different mental activations, mental functioning of the brain. Also language. For example, in your country, there are several languages. That's the reason that we are trying to talk in English for all of you. Sorry for my English, because my native language is Spanish, so I try to do my best with English. But language is very important also in the way the brain activates. I ask you to see to this TED Talk of Lera Boroditsky, that in this video, she talks about how language shapes the way we think. And it's really a very interesting talk because, for example, some languages have a special words for the different directions. For example, people who lives in very hard environments with animals that attack them or something like that, they develop special words for spatial directions that are associated with cardinal points, for example. So they didn't thought in terms of left, right, but north, west, south, something like that. And the process of meaning of language inside his brains are completely different from us. Of course, other cultures issues also influence how the brain works. When you go to the details, of course, all languages and all cultures have some common aspects, but in the detail from a particular brain from one person, all these aspects are important to take into account. And well, even for one subject, mental state can change between this recording session. You can be tired or hungry, or you can be distracted for some things. So even for the same person in different moments, you have signals. That's the reality of the thing. And some databases have also many recording sessions. That's an important issue, but it is very difficult and very hard to record databases, for example, with many subjects and with many sessions. But if you can do it, it is interesting because you can capture the variability intra-subject with this type of recording. Also, sensor location differ between recording sessions. You generally have some type of cap that have predefined location, but even with that, when you put the cap, the location of the electrode is not exactly the same from session to session. So that's a very small difference in location produce perhaps important variation is in the signal you are recording. And well, of course, brain dynamics are non-linear and non-stationary at all time scales. So this is another problem. Here is a picture from two brains. I think that they are twins. One has autism and the other not. And if you see the brains, it's difficult to find the difference between them. So this is only for trying to think about the difficulty of this task. Because one problem here is in the neuroscience of the last years, with all these techniques available to analyze and take images of the of the brain and the process inside. Sometimes there is some type of reductionism because you think that taking activity or registering activity in one particular location of the brain implies directly that you are doing some type of task. And this is an oversimplification because the human behavior is really very complex, and human process of producing, for example, a speech involves not only one part of the brain. Really, we will see this thing. All the brain is involved there, but sometimes you are only focusing in one small area of the brain to see what's happened there, and only you can see the activations. There are much other information. For example, how one particular part of the brain is connected with another part of the brain, what it called the connectome. That's very, very, very useful information also. So it is important not to reduce the problem only to what you can measure or what you can see from images. Well, here I present you some images also from different brains. Here at the left you have a particular brain image and some different views of the brain of one individual. This is the number inside the database of this particular subject. And here is a average. Here are average images. It's like an average brain with 440 subjects of this database. So look at the difference between the average brain and the particular subject brain. So some things are common, but other details are really very different from subject to subject. This is only to remark again the high variability we have. This is only images, but you can also think in the functional aspects of the brain also. This is anatomically, but also you have similar things in functional mappings of the brain. This is a very, very interesting project, Human Connectome, that you can surf there and look for some images and try to understand how this complex organ works. Even signal to noise ratio is very, very low in general. So sensitive measures are hard to obtain. We just talked about this issue also. Relevant brain activity is small compared to interfering artifacts and all what it called the background activity. And specific measures are even harder to obtain because you generally have coarse grain sensing. For example, in EEG, you have a spatial resolution of about 1 centimeter, and between two electrodes, really, you have many thousands of neurons in the cortex, and also you are trying to record the signals in the surface, but you have also really the phenomenon is produced at level of the cortex, and we have many layers of skin and bone there, so the signal is really affected or filtered by all these layers of tissue. A large collection of neurons are involved in many different activities, not just one, and in many different areas of the brain, as I already told you. And underlying phenomena are also highly diverse and rich, and derived measures are still nowadays are still poorly understood, and not always clear what to look for in the signals. Well, a consequence of all these, sophisticated signal processing and classification methods are required. Although classification algorithms can be developed offline, that's the main research part of the work is offline, not online. But only online analysis can yield solid evidence of BCI system performance, because it is not the same that the person have some feedback while using the BCI system, that only offline processing of, for example, speech-related brain signals and the classification of them offline is different from online working of the system and the function of the brain also. So that's the reason that BCI system must be calibrated before they can be used. You can record signal from many subjects, but at least you have to calibrate the BCI with the particular person that will use it, because of all the variability I have just told you. Calibration should entail as much information as available, not only example data, but also prior knowledge. And you can use large databases. There's now many important issues to take into account, like transfer learning techniques, because you can try to use the useful information from the other subjects to the subject that will use the brain-computer interface. How you can do that? That's the challenge. So we have to think in new ideas in order to attack this very hard problem. And in the last years, with all this new area of deep learning, that is really an advance in machine learning and neural network performance in different applications. That issue, new algorithms developed in the last year, coupled with the availability of vast amounts of experimental data, and also high computational power, allow new levels of performance to be reached in this task. And here I cut and paste several works and papers of the last few years. So this is a very hot topic. Many papers and works arrive every day. So we can try to give you a broad picture of these works that try to solve this hard problem. Well, this is all for my side. I don't know if you have some questions. In the background of this slide, you can see Santa Fe City Bridge. That is very pretty bridge. If you come to Argentina, I can show you the places. This is some of the people working in my lab, in my institutes. So this is The work I will show you is not only my work, but the work of a group of people. So thank you very much, and I expected some questions.
Thank you, Professor Ruffiner, for that wonderful talk. Maybe some questions from the participants, questions, clarifications. Any of you?
Hello, am I audible?
Yes, Dr. Nitya. Yes.
Yes, sir. You mentioned that because although we'll be developing algorithms which are offline, their testing online is what is required more in this area. And how will that be? How difficult is that, considering that there is a lot of variability, and we would not have seen, even when we use deep learning, we would not have seen many. During the training, we would not have seen many brain signals or EEG signals which we'll be seeing at the testing time.
Yeah, I hear slow. Can you repeat, or Professor Prasanna, if you hear, you can.
If I'm Professor Ruffiner, I will try to repeat. Nitya, you can clarify it if I'm telling properly.
Yes.
So what she mentioned was, since there is so much variability in the EEG data, how easy or difficult? Sorry, Nitya, I also did not hear carefully.
Yeah. Sir, is it audible now? Better? Is it better now?
Yes.
Yeah. So I was asking, since there is a requirement of processing the real-time signals, real-time EEG signals, even though we are processing, developing algorithms using offline data, real-time signal may have very different characteristics than what we have seen in the training, say using deep learning methods. So how will we tackle that difficulty? That is
so for real-time processing, since most of the algorithms are trained offline using the previous session data, so how do we tackle when we want to evaluate these algorithms in real-time data?
Yes, that's a good point, and it's really a problem with BCI technologies, especially in this area of cognitive speech processing. But the problem is so difficult. So most of the research try to solve the problem offline because that's easier. Of course, when you go online, the performance degrades.
Yes.
But it is very difficult to try to solve the problem online directly.
Yes.
So many of the research try now to solve the problem offline, and perhaps in the future you can enhance the techniques in order to work online.
Okay.
That's the state of the art now. So it's really a big step from offline to online. That's also in classic BCI, but in classic BCI there are a lot of work there. But in this new area, very few works work online. Really is an open issue. So it is difficult for me to answer with a detailed particular data because it's an open point now for research.
Oh, okay, sure, sir. Thank you.
Thank you.
Any other questions? Any of you?
I think that there are many possibilities to explore between offline and online. For example, some mapping techniques nonlinear mapping, trying to map what you get from offline data, how to map it to online activities. For example, you can use adversarial networks or transfer learning or something like that. But it's still an open research issue.
Okay. Thank you, sir.
So any other questions?
Sir,
Govind, please.
yes. Sir, in one of your slides, you mentioned that you have developed one. Your group has developed one database which is open source. Can you just elaborate what kind of database on EEG or?
Yes, both. We developed both two databases. Both of them are EEG databases because we think that they are very good results with ECOG, intracortical electrical resistors. But that's invasive and with very high cost equipment there. And problems with the patient and all that. So I think that the most challenging and useful thing is to try to decode information from EEG. So both databases are EEG databases. The first database is for imaging speech, or the subject try to imagine the movements that generates the speech. So that is more related with motor imagery. And the other database, the new one, that the paper was published, I think, last week from Nature, is inner speech database from EEG also. The difference between the two databases, the first database, it has a few electrodes and perhaps a more simple device in order to record the signals. But electrodes are in a specific location near the auditory and the motor cortex. And in the last database, we have many electrodes, hundreds of them. So you have a better spatial resolution in this database. Most of them have 10 subjects, but we will discuss all the details during the course. And the idea is that you can put hands on all of this data.
Oh, okay. Thank you, sir.
Thank you.
Any other questions? I know, Professor Rufina, you will clarify in later sessions, but when you mentioned chance level performance, for almost all tasks using EEG, we have this chance level performance only?
Very few works can have results really very far from chance. With few words, yes. In the last, I think, 1 or 2 years, there are some few works with better performance than that.
Okay.
But it depends on the data, it depends on the subject. You also have very variability between performance, between subjects also in the database.
Okay.
Because you told the subject what is the task he will do, but you really don't know what happens inside his brain. He can be distracted by personal problem, or he can be boring or tired or something like that. So it is very difficult to know if he is really, or he or she is really doing what you told to do.
Correct. Correct.
All of this complicates the solution of the problem. But I think that nowadays deep learning techniques are really very powerful. We need more research there in order to develop specifically techniques for this problem, I think.
Okay.
Because most of the works try some technology, some architecture that works well with speech, and they try to put in this problem and multidimensional characteristic and all of that. It makes very different the approach. So it's still an open research problem.
Okay. Thank you.
But
Thank you.
I want not to. I think that my idea is to want the difficulties, but not to put you the idea that this is impossible to do, because in that way we have to close this and get to other problems. Yes, it's a challenge. It's a challenge, I think, to try to solve this problem.
Thank you very much. So, okay, if there are no more questions, thank you, Professor Ruffiner. So we will handle the tutorials. I think you have spent 2.5 hours. Please take care. We will proceed with the tutorials. Huh? Thank you. Jagabandhu?
Yes, we'll start. So, good evening to all. Am I audible, Lala? Hello.
Yes.
So, I am presenting my screen. So my screen is visible.
Yes.
So as already Professor Ruffiner has mentioned, so today we will go with basic Python. It will be just the introduction to Python, whichever will be applicable for signal processing and machine learning based research work, and about the introduction to some signal processing tools or speech processing applications. I used to cover on the third day, and tomorrow we will go with this pre-processing of EEG signals, and final day we will fourth day and fifth day we'll go for some classification task with some EEG task. So let's start this basic Python tutorial. So as we all know, nowadays most of the approaches, most of the frameworks.
Please zoom in, sir. Zoom in a little bit.
So is it fine now?
Yes, sir.
So as we know, all know that most of the applications like EEG signal processing and speech processing, many of the tools has been designed in Python and open sourced in some GitHub and different portals. So earlier people use MATLAB. Then nowadays people are slowly moving towards the Python as it is open source and it is freely available, and most of the packages and libraries which will ease out our task has been available in the Python library. So it is better to learn some basics of Python, and if someone has not much exposure to Python, they can this tutorial can help them to go ahead and start with Python. So I think today morning we have shared already this Python notebook already with the participants. So if you have with us this, you can download that and you can open either through Google Colab, or you can open through Jupyter Notebook, and parallelly you can run with me. Okay, so in this tutorial we generally cover basic Python, so different kinds of data types, and even the data containers like list, dictionary, and sets and tuples. Then later we'll go to functions and classes. And next, the most useful library of Python, it's give a feel like MATLAB, like NumPy, which will have very good processing of matrices. It terms as arrays, array indexing, data types, array method, different broadcasting. It supports that NumPy method. And the next toolkit is Matplotlib. It is similar to a plot tool like MATLAB have. So we can do different, we can plot different graphics through this Matplotlib. And another one is data frame. It's a similar kind of work to do like MATLAB table function it have. It will be good for processing the Excel files or CSV files, all this. So first we should know where we can execute these Python scripts. So the first part is we can write a script in Notepad, and we can execute in the terminal. The next case is Spider. It's like a editor, like MATLAB editor. We can use that Spider to run your Python course. And the third one is Jupyter Lab, or Google Colab, or this Jupyter Notebook. So which will give a documentation kind of view what I am presenting now. So even MATLAB have also a similar kind of set of .mlx file. Okay, so let's me start with some small exercise with different ways to execute a simple Python code. Let me open my terminal. So I will increase the font size. So I think it is visible. Let me just create a folder. Go inside that. I will just create a file, demo.py. Now I will, what I have created, I will go to home. I have created some Python underscore tutorial demo.py. Now I can open it. I can write my code here. I just increase the font. So hope this is visible. So I am here just importing NumPy library as NP. PLT. Now I will just take a find function, some 2 into x plus some type type, and then I can print this value of y, and I will try to plot this plt dot plot y comma y plt dot show. Try and see. Now, once it's done, I can now I will run this script by writing Python. This will be my demo. Sorry, switch to the definition. Okay, so let me x equal to np dot array range, and it will just create a array from 1 to 10 with the increment of 1. So you can see can able to plot this with some 0 to 10, and we have taken some 2 into some with plus 5 or something we have taken as a affine function. So the values we are getting this, and similarly it has plotted this. So this is the one way we can write our Python codes in the notebook, and we can run it through command prompt. Another one way is we can use some toolkit called Spider. So this will be look like this. Maybe I can go to this route to the same folder. You can open this, and now if I want to run this script, right here your code also, and now if you want to run it, you can directly just run it, and you will get the figure here, and the output values you can got here. So another way is like this Jupyter notebook. So I can open one Jupyter notebook here. So it will open like this. So I can take a new Python 3 file over here. So it will create like this. So either you can, if you want a code block or markdown block, you can take. You can write your commands here, anything. Suppose I want to write Python code to plot a affine function. So put control enter, it will give this. Want to add another, you can add here. So this is my code block. So either I can write or I can copy paste from this here. Or Use Control Enter to run this. You can see the output here. So this is 3 ways you can run your Python codes in your system. So if you have any doubts, you can ask here, or else you can go. Anyone have any doubt? So if no one have doubt, let's go to the next part. So here I want to show So I want to show a simple example to do a quick sort by giving some numbers. So we can see how it is done by Python. So this is the way how we can define a function. Okay. So my task here is I am giving some number array called 987654321. And I want to do the quicksort. So as per the rules of quicksort, what we will do, we will do the pivot we have to declare, which in the middle of the, whichever in the middle of the array. Okay. So we are taking as a pivot, and the next one, it is taking the left. It will take all the elements which whoever are the less than the x, less than the pivot, it will take as x, and whoever are the same as that one, it will take as a middle. And whichever is the higher than that one, it will take as the right. Okay, so if we can, if I'll run this, maybe you can, people can able to understand this. So let me first, yes. So as the middle of the element is 5 here. So I am taking whichever the values are lesser than the 5 are the 4, 3, 2, 1. Same as 5 is 5, and whichever are greater than is 9, 8, 7, 6. So it will go recursively. It will call the same function. So after that, we can get the quicksort as 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So this is just an example how we can get this. So next. In general, there have many versions are available for Python. There will be Python 2 and Python 3, but currently Python 3 are largely used. And when you are dealing with Python, maybe people have to be somewhat careful, because whatever the versions you are using, you have to be more careful on that version, because the previous versions, whatever you have written the code, some of the functions may be depreciated in the current version, and it may not work. So on that case, you have to be careful when you are updating your Python version, or you are degrading the Python version. So on that way, you also have to be managed to your coding strategy and all this. So basic data types is like other languages. So it also have numbers, and then strings and booleans. So here, suppose I am taking x as a variable as a number, I can define it like this, and then I can print it, and I can also print the type of that one. Okay, so in this case, this is an integer type variable. Okay, so if I will take instead of 3 dot, this will be a float type. You can see this will be a float type variable. Okay, so now you can do addition, subtraction, multiplication, and exponentiation with this. And similar way, you can do the pre-increment one and pre-multiplication. So now in this case, you can print multiple types and type of that, and y plus 1, y is to the power, y to the power 2, you can write like this. by multiplication with 2, you can write like this. Okay. So now the next data type will be booleans. So like logical values at true and false. So I am defining T as a true and F as a false. Now I can do some logical operations like AND, OR, NOT, and XOR through this. So as we know, like true and false, if we do a AND gate, we will get a false. True and true or false, we will get a true. Not true is false. And if if I am telling some if statement kind of T not equal to F, this is actually true. Actually, true is not equal to false. So that's why this logic is true. Okay. So the another data type is string here. So in generally, if we define a string like hello and another variable as world, and if we want to concatenate it, we can concatenate it like this. Either you can this I am telling hello 5 because length of the hello I am printing here. You can also print something else. If you want to print world also, you can do it. So in generally, the string concatenation has been done like this. Generally, if you want to join some path where you can some web files or easy files or something is there, so you can write your string concatenation like this, and you can invoke that data path. This is some different ways how you can do the concatenation. So this is different functions which Python supports. We can capitalize the string and we can do the uppercase. Okay. So similarly, write justify, center, justify, and we can replace with something. And so these are different ways. Okay. So the next we can go to the containers. So there are different type of containers which supports Python. So first one will be the list. Then we will go for dictionaries, set, and tuple. So here list, generally the list is defined with square brackets, any list variable. So access is a list. I am defining 3, 1, 2 as the list. So you can print. If you want to find any element of the list, you can do it like this. Access of 2. So -1 is generally the first element. 2 is the -1 is the last element. If you put 0, 0 will be the first element. Similarly, the list supports different data types. You can use different data types in a single list. So here, as 3 is an integer, but 4 is a string kind of type, you can use it like this. So suppose your string length is 2 here, 3 here. If you want to increase, you can directly write append and you can add something here. And similarly, that pop and push, if you want to delete something, you can just pop out that. So here this bar has been popped out. Now if you print the access, this is only the 3, 1, and 4. So now next one is the slicing. How we can slice the list. So here it is some generating some list of range 5. This will be some 0 to 4 numbers. So it is printing here. I am taking 2 to 4. So 2 means it will start from 2 and it will end at 3. So be careful on that. And this is where I want to start at 2, but we want to end. We want to get till the end. Okay. So you can see here 2 to 4. It's only 2 and 3. These 2 elements. Okay. So now next one will be 2 and 2 to all. So it will start from 2 and it will go till the end. 2, 3, 4. Next one will be starting from 0 to 2. Okay, so 0 and 1 it will be printed here. So -2 means all. It will be print the all values 0, 1, 2, 3, 4. Colon -2 means it will till the third position it will print before 2 actually, end -2. We can define it number of 2 to 4 will be 8 and 9. Okay. So the next part is loop, how we can deal with.
Sir, I have a question.
Yeah, please.
Sir, are you giving the index or the in each slicing? 2 to 4 is the index, or
Correct.
do you have?
No, this 2 to actually num is a variable, okay, which is a list, which is a number from 0 to 4, correct? 0, 1, 2, 3, 4. So now I want to take only the elements 2 and 3. Okay, means this third position and fourth position. So in this index will be 0, 1, 2, correct? As Python follows 0 indexing, so it will start from 0, 1, 2. So it will start from 2, it will go till 3. Is it clear? Stella, is it clear? Hello.
Yeah.
So, okay. So then we can go to the loops. So we can define animals as some cat, dog, and monkey kind of thing, and you can write a for loop like this. Actually, the syntax of for loop is like this for Python. For I in animals, colon, you can print I. Okay. So every element of that list will be printed over here. So next part is if you want to print with some numbers, you can edit like this: %d colon % of s. Okay, so index +1 comma animals. Okay, so index is starting from 0. So 0 + 1, 1, 2, 3. We are getting cat, dog, and okay. Then list comprehensions. So comprehensions means means some addition, multiplication, squares, and how we can do with some lists. So here we have defined this number as 0, 1, 2, 3, 4. So if you want to do the squares and we want to print that square, so square I am initializing as an empty matrix here. So for x in numbers, squares dot append x square. Okay. So this double star is generally used for squaring operation. Then print squares. So it will print the 0, 1, 4, 9, 16. Okay. Now in one line also you can write the same code. Squares equal to this for x in nums. Okay. So in single line also you can write this. Then list comprehension also contain conditions. You can write some condition over there. That if it is even number only, you do the square, else you don't do. Okay. So like 0, 1, 2, 3, 4 here, I want to do x square wherever this dividing by 2 or remainder is equal to 0. Okay. So I am now getting 0, 4, 16. Now the next part is dictionary. So this is very important part to deal with different kind of databases actually. Maybe tomorrow's session we will use it very heavily, this dictionary variables. So d equal to, suppose here this in general list the index will be 0, 1, 2, correct? So in this case we can define our one index. Okay, so here I am giving cat is my index. Cat, this index have a value called cute. Okay, Similarly, dog is a index which have a value called query. Okay, so now I am printing D of dog. Okay, similarly, cat in D. Okay, so cat in D, what it will tell is this index is available at D or not. Okay. If you want to add something, you can just write D of some index name. Here in this case, I am using fish as weight. Okay. So if you print it, you can. Okay. Similarly, monkey is not there in the list. If you want to print, it will throw an error. So if you insert that and then print, it will. So insert this. Some value I can write weight. Now if I will want to print, I can print it. Now it is telling get an element with a default print called NA. If it is not there, then it will show as NA. Okay. So as it is there, so it is showing weight. Now I am deleting this fish entry. Okay, now I am printing this. You can see if a fish is not there, it is showing not applicable. So it's also easy to, if you want to iterate it over the keys. Okay, so generally this indexes is known as keys for dictionaries. So for animal in D, it is just showing D of animals, legs equal to. So person have 2 legs, cat have 4, spider have 8. Okay. Suppose. So now you can print it like this. Person have 2 legs, cat has 4 legs, and spider has 2 legs. Now this is a similar one. Either you can do it like this, or you can write for animal, comma legs in D items, and you can print. Okay. Now dictionary comprehensions. Suppose I have numbers and I want to print only the numbers having only the even numbers I want to print. So you can write X. So X is suppose my key and X square is my value. Okay. So in this case, I can print the values of my even index values. Okay. So 0 have 0, 2 have 4, and 4 have 16. So the next is sets. So in generally, this is the way we can initialize a set. Okay. So animals equal to cat, dog. So we can print these values. Is it present? It will say true. If it is not present, it will tell false. So you can edit, and after that you can see is it available or not. You can see also the length. So here I want to add cat, and I want to see the length. Then I want to remove it, and I want to see the length. Okay. So now next one is how we can do the looping with this set variable. So as like lists and dictionary, we can also do looping. Looping with this set variable. Suppose animals is cat, dog, and pigs. You can write idx animal in enumerate animals. Okay, so then you can print this. Then the next one is list of list is also like dictionaries. We can easily construct some set comprehensions as like set and dictionary. Here also we can do some comprehensions. So in int x for x in range 30. So it will give some 0 to 30 values. If you want to do the square root for x in range 30, it will give the square root of that. Now the next one, which will be mostly used in nowadays in deep learning applications for data loader creation, mostly for PyTorch and TensorFlow libraries with PyTorch and TensorFlow libraries. So what actually how it is different from earlier your list and dictionary, whatever we have read till now. So this is one which can support some kind of sets as a key. Okay, so earlier we have seen only one key is possible. Here we can take set as a key. So this is the advantage of tuples. Okay. If you want, suppose 0 1 as 0, 1 2 as 1, so you can create a tuple like this. So it also supports different data types. Now next one is functions. So how we can write a function. We already have covered the data types. Now the functions. Suppose I am defining a function called sine function or signum function. If x is greater than to 0, that will be a positive value. If less than to 0, it's negative, or else it is 0. Correct? So I am writing for x in -1, 0, and 1. Suppose I am giving some 3 values, -1, 0, and 1. So print signum of x. So if -1, this will be giving negative, 0 for 0, and 1 for 0. Okay. Another function we can just define like that by taking a input argument, name, and loud. I have written the two things. This is actually if I will not pass any value, so it will take as a default value as false. Okay. So in this case, if you see my if statement, so in the first case, print, I am taking if loud. So loud is true, then it will print this, else it will print this. Now I am calling here this function, hello Bob. So I am giving the name, but I am not passing the loud information. So by default, it is taken as a false, and it will print this statement, correct? So next case, I am taking loud equal to true, so it will print me this. Okay, so if you see this, I am giving as input as Fred. It is giving it uppercase of this one. Okay. Next one is the classes. Again, it is also very useful. So if you see inside the classes, we can actually define multiple functions. So if you have any kind of global variable you want to pass to the class, so you can define these values over here. So self dot name equal to name, or if you want have any other variables or global variables, you can define here, and you can mention here that these are the values of, or you can assign here. In this point, you can assign in the init part. And suppose another function is some greet function over here. Okay, so if there have similar, like earlier I have taken this loud, if it is true, then it will print this, else it will print this. Okay, so in this case, I am initializing my class is like this, g equal to greater Fred. So Fred is my name, it will go like this. So if you want to call without any argument, you can call it like this, and that function available in that. So dot operator is generally, if you see this g is my object. Dot operator will be used to call my functions present in that class function. Okay. So this is the way we can use the class. Next one, we can go to the NumPy. So we already have seen some applications using NumPy. So we can, NumPy is the library and we are assigning as NP. NP we can use throw NP throughout. So the first part mostly used is the array with NumPy. So the way we can define a equal to np dot array 1 2 3. Okay, so it will define a value a equal to this one. Then I want to print the type of a. I want to see the shape of a and the elements I want to find 0 1 2. Okay, now I am assigning here a0 is equal to 5. Now I can print a. Okay, so if you see, initially this is a class of NumPy array. Okay, this is my type. Okay, so 3 comma is the value of the shape. You can see a dot shape is 3 comma, and a0 is 1 2 and 3. And once I assign 5 over there, now print I 5 to 3 I am getting here. Okay, now I am defining another variable called b as a matrix. Okay, so if you print it, you will get like this. So if you see the shape and the elements of that, you can invoke it like this. B00 is 1 in this case, 01 is 2, and 10H 4, correct? So 1 2 4 way. Now how we can initialize a matrix with all zeros? So np dot zeros we can use. This is my size 3 cross 3. I have to place it like this so that I can able to generate this. Similarly, np ones 1 comma 2 is my size. All ones I can create like this. So this full is if I want to give some number, want to create with some matrix order. Suppose in this case is 2 2. I am just change to 4 2. See, all values will be 7. This is a 4 plus 2 matrix. Okay, so I is like a diagonal entry. Okay, so 2 is my dimension of this one. So if the dimension is 2, I can create a identity matrix of 2 dimensions. Okay, now this random is just to create a random matrix initialized with some random value. So random generally samples from uniform distribution. So the next part is array indexing. Suppose I am defining A as NP array 1 2 3 4. So you can see for a row I just want to write the values in a square bracket, and if you want to go for a column, you have to initialize another square bracket and you have to differentiate with by comma, with this by comma. Okay, so now if you want to define B as another matrix which is a part of A, I am taking all up to 2. 0 1 2 up to 2 means this will be the first 2 values it will take. 1 2 3 only it will take 1 and 2, first and second element of. So I will take this row wise 0 1 and column wise 1 and 2. Okay, so let's see how it is coming. So my matrix is 1 5 9 2 6 10, this one. So I have choose that I will take only 0 and 1 in the row. Okay, and in the column it will go for 1 and 3. Okay, 1 and 2. So this 2, if we see 2 3 and 6 7 is my output. Okay, so this is another way, similar way you can do the slicing. So this is a 3 cross 4 matrix, how you can define. So you can find the row and 1 to 2 comma all. So how we can find all these values? This is just different way representing the same. So this is actually interesting part you can see over here. So in generally, if you put it as an array, it will give 4 comma nothing. So if you want to increase the dimension in some direction, or so generally it will be useful for matrix multiplication kind of thing, because we have to satisfy the dimensions like 1 cross 4, 4 cross 1. Okay, so on that cases these forms are useful. Similarly with column mode. So if some matrix is 1, 2, 3, 4, 5, 6 in this case, so if you print only this 0, 1, 2, and next one will be 0, 1, 0, 0th position. Okay, so then the values will be printed here. So my A matrix is this one, is a 3 cross 4 matrix. Now I am taking the values from that. Okay, sorry. Okay, so this is just a yeah. So if you see the print 1, 2, 3, 4, 5, 6, this is a 3 cross 2 matrix. So I am printing what? 0, 1, 2, and 0, 1, 0, okay, which will give me a swap of 3 comma. Okay. Similarly, 0, 0, and 1, 1. If we see 0, 0 is this one, and so now if I will define another array called 1, 2, 3, 4, 5, 6, this one, and I can print it like this. So B, another array, I am creating 0, 2, 0, 1. Okay, now I want to print A, NP arrange 4. So NP arrange 4 will be the value 0, 2, 0, 1, 2, 3. Okay, and I want to give and another value are 0, 2, 0, 1. So it will print these elements of this one. Okay, this is X index and Y index. Now, if you want to increase these values as with 10, you can do it here. So similarly, you can do Boolean array indexing over here also. So suppose A is 1, 2, 3, 4, 5, 6, and I am telling that this Boolean index A will be greater than to 2. If A is greater than to 2, then only it will be true, or else it will be false. If you run it, you will get wherever the values are greater than 2, you will get as true, or else cases it is false. So if you see this one, case it is false. Okay, and 2 is also not greater than to 2. This is false. All other cases is true. Same thing you can invoke here. You can put Boolean index. Wherever the true values are there, it will only give these values. Okay. Or you can directly write wherever A is greater than to 2, you just ignore that. Okay. Now, this NumPy also have different kind of data types. So first case it is integer, next case it is float. In this case it is integer with 64-bit. So this is the different way we can typecast our variables with NumPy. Now, with different mathematical operations, we can also do with NumPy. So x and y, now I am printing x plus y, first case, and also you can write np add x comma y, both are same. Similarly, you can do subtraction, multiplication, division, and square root. So another thing is over here is multiplication. So you can do dot product. Dot multiplication means it will do the pointwise multiplication over here, multiplication and addition. Okay. Similarly, x dot v also you can write. So x is a 2 cross 2 matrix. You can do a vector multiplication with this one, pointwise multiplication, and you can write the output whatever it is. Now we can go with addition of the values. Suppose we have a 2 cross 2 matrix, we can add it in two directions. One in the row direction, another one in the column direction. Okay. So if we put x is equal to 0, it will add it in the column direction 3, 1, 4, 2, 4, 6. So if you put x is equal to 1, it will do in the row direction different way. So transpose we can do with x dot t. We can do the transpose. Next is broadcasting. Suppose x is an array 1, 2, 3, 4, 5, 6, 7, 8, 9, and this one. He is another array. If you want to, y should be the another array which will be like x, but all values are empty. So will all 0. Next, you can take some values from x, you can add with v and put as y. That you can do with a for loop this way. So tile is like a repmet function in MATLAB. So I want whatever the v values will be there. Like in this case, we have defined 1, 0, 1. This will be repeated with 4 cross 1. Same values, same matrix will be repeated. Okay. So later I can edit, or you can do some other operations. The same case only. Now another thing is you can reshape your matrix in different way. So V is suppose NP array 1, 2, 3 and W is of 4, 5. Now you can write print NP dot reshape V to 3 cross 1 and you can multiply with W. So in generally this is some 3 comma, the shape is this one, and W shape is 2 comma. So if you want to do the matrix multiplication, you have to reshape it first. This is the case of vector addition. You can do the transpose and edit. You can reshape it to 2 cross 1. Okay. So W is initially 50. Some 2 comma dot. So it will be converted to 2 comma 1. Okay. If you reshape it, then you can edit to this. Similarly, you can do the multiplication. Then the next part will be the matplotlib, which you can use for plotting purpose. So here, if I will see this, I am taking arrange, NP arrange, which will take 0 to 3 with a step of 0.1. Okay. So print x dot shape y equal to np dot sign x pi. Okay, so pi x I am taking as a my this one. So your sampling frequency is half. So y equal to I am taking this. So plot x comma y. Okay. So I am just generating some 30 values. So you can see this. The sine function and plot this. You can use x comma y. So you can take sine and cos, and you can plot it one by one, one overlapped with another, like a hold on function in MATLAB. Similarly, this also supports subplots. Sine and cosine. Next part is pandas data frame. So if you have any doubt till this point, you can take after the take over. So I have no doubts. Can go forward. So
There is a doubt in chat box.
okay. What is that? Dot operator in class. Explain. Small. Which one, Sogata?
Sir, the dot about.
Huh. We'll go. Okay, so now I can do one thing here. I will take the value of x and y. Now you can print x. Print y. So this is my print x and print y. So if I want to do, suppose.
So that is not np dot dot. That is a, you are showing some class dot g dot class.
Oh, you don't want this one. Okay, so let me go there. Yes. So if you see here, G is your object, correct?
Okay.
Okay. So this function is a child function of that class, correct? So if you want to use this function, whichever is defined in this class, to invoke that, you have to use dot operator. Okay. That object, after that you have to use the dot operator, then the child function. Okay, is it clear?
What is the role of G?
Huh?
G.
G is an object.
Okay,
So
when
you call a class, no, it will create an object called G, or anything. You can give any name. You can put H or something.
Sir, object means reference, right?
Yeah, reference of that class.
Okay.
It's not actually reference. Maybe you can think on that, like no issue. Okay.
Okay.
It's fine.
Yeah, and one more thing, sir, that in matrix you showed, sir, a matrix row np dot arrange 4 comma b, where that one I didn't get.
np dot arrange where this plot matplotlib.
No.
Huh? Where?
Yeah.
This one.
Yeah. Above that.
So if you do np dot arrange, what actually it will do? It will take values from 0 to 3, correct?
0 to 3.
So now let me first print here what is A. Okay, this is not the A, no? This is your A, correct? So let me print here first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, correct? Now, what I am telling, NP arrange for comma B. What is B here?
Column means here.
0 to 0, 1. Okay. Now, if you take 1, 2, 3, 4. Sorry, 0, 1, 2, 3, correct? NP arrange for 0, 1, 2, 3. So this will be 0, 0, okay? 0, 0 is this one, plus 10. This will be 11, correct?
Okay.
Okay.
Okay, got it.
This is the way. Okay, so let me go to the pandas part. Any other doubt anyone have? Okay, so to install panda, you just have to install like this. Either you can write the same thing on your terminal, or if you are using Jupyter Notebook, you can write like this to install this. It will not take much time, few seconds. It will install this. Either using pip or you can using Conda, you can install it. Okay, if you have Conda. So along with NumPy, I am also here invoking the pandas. So that if there have some kind of series of data, like in this case, I am taking my number array is np.random 4, some 4 numbers I am taking. So next one I am taking this panda series. Okay, np random for same numbers I am taking as a panda series data. If you see the difference between two, this is my NumPy array, here is my panda array. Okay, so it's like a tabular format. Okay, 0, 1, 2, 3 index, and these were the values. Okay. So if you, instead of 0, 1, 2, 3, if you want to give A, B, C, D kind of index, you can give your index like this. And also if you can also invoke that B values as like this. So what are the indexes available? You can also able to see. Okay. So suppose a dictionary A is 1, B equal to 0, and C equal to C is 2. So you can print the dictionary. Similarly, in panda series, you can print the same dictionary as like this. So the dictionaries you can convert to panda series. Okay. So you can do some
Sir,
yeah.
Hello. Yes, sir. I'm little bit confused in series, list, and dictionary. Can you elaborate once?
Yeah.
Only?
So the list, if you go, so in generally in the list, it will be inside the square bracket, correct? And it have index 0, 1, 2, 3, correct? You can't change the index. Is it fine with series? First one with the list. Second
Yes,
one
sir.
is dictionary. Okay. In the dictionary, you can give any name as an index or any key and value, it kind of thing. Okay. With respect to key, you can define a value. This key may be your numerics, key may be your any names, key may be your string. Correct. So it all will come in a dictionary format. Inside the colon bracket, you can put it. But when you comes to series, okay, so it will be create like in a tabular format. Okay, it will be better to when you want to go to write in a CSV file or in a Excel file, no. So you have to first convert it to series, then it will be easy to put it in the Excel format or something. Is it clear? All three?
Sir, actually thing is that same as in the dictionary, in the series also, we can index it with any key value
Correct.
and give the value.
Both are same. If you see here, let me go to Yeah, so this is the case, correct? So this dictionary in generally we can invoke it like this, correct? And when you convert this
Yes, sir.
into series, it will be like a tabular format. It will show like in table. This is the only difference. There have no means storing difference. Only the viewing difference it have. Is it clear?
Okay, we need to take care only while we are accessing the CSV file.
Because when you read this,
Okay.
it will be very difficult to without pandas. It will be very difficult to get these values, because it also have some. I will go down and show you that we can say what is it, column names kind of thing. No, it have different values. Like here A, B, C. In another column name, it may have number. Another column name, it may have some other strings. Correct. So this kind of operations can be easily done with pandas. Okay.
Okay, sir.
So now, suppose it's a dictionary. If you can see, first column has these values. Second column has these values. Panda data frame of D. It will show like, see this first column. This is my column name, second column name, and this 0, 1, 2, 3 are the indexes, and these have different values. Okay, so similarly, this is actually a task how you can insert this values into a panda data series. Okay, so you can write like D equal to house area, whereas panda series 1, 2, 3, you can insert your values here, whatever the area values, instead of 1, 2, 3. In the index, house 1, house 2, house 3, correct? And house 2 have values. House 2 instead of house price, actually this one, you can change it to on your page. So once you run it, you can get house area and house price. Some values you can put, whatever the values are there. So this is the way you can create a data with this pandas. Now, if you want to import, you can directly import pd.read.csv, a CSV file. Okay. So if you see what are there, df.head, you can get many values. So you can access with some. So total rooms, if I want to see these values, so you can see these values like this. You can do all the operations which is supported with NumPy. It also supports with, this pandas data frame. Okay, is it clear till this point? Okay, so next you can go to PyTorch. So PyTorch is mostly used for deep learning applications. The best thing of this one is actually once we grow on doing some operation like multiplications, additions, linear or nonlinear operations. So it will also stores its gradient values with that torch variable. So it will be easy for when you are going for back propagations. So with that graph, we can go back and update the values with the gradient values. Okay, so for that, generally, torch is so useful. If you are even whenever we are going and doing something like gradient based learning kind of thing, even it's from starting from regressions to neural networks. Okay, suppose here I am defining a torch.tensor as 4 dot. So this will be my floating point values 4 dot. So I want to print this. This is a tensor value. Okay, so next one I am taking a vector as a tensor 1, 2, 3, 4. So wherever if a single value is of floating type, it will take all the values as floating type. Okay, and next one is a matrix. Okay, so next one is a 3-dimensional array. Okay, how we can define a three-dimensional array, as you can say. So next one, you can print these values. Now, if you want to do some kind of arithmetic operation, okay, so you have to if I defines requires grad as true, so it will automatically take the gradient values. So I can show you how it will. So x equal to 3, w I am taking as a 4 and gradient is true, b is 5 and it also gradient is true. Okay, now what I am doing here, y equal to wx plus b, which is what is y now, this is 17. Okay, so the gradient function is add and backward. Okay, so now if you see, y is this one, I am doing a y backward. So once I do this y backward, what will do, it will calculate the gradient values. Okay, so x, as we have not defined anything, it is known, and other cases dy by dw is 3, dy by db is 1. So if you see here, initially this w values we have taken as 4 and b values is 5, x is 3. So if we do dy by dw, it will be my x value, correct? So x value is 3. It will be computed here and written here. Okay, so if you print this w dot grad, it will give me the, with respect to w, what is the gradient value. Similarly, with respect to b, which is what is my gradient value, it will directly give. So this is actually airs out your backpropagation algorithm. So that is why people have largely used this PyTorch package for deep learning applications.
Sir,
Okay, so
hello.
Yeah.
Sir, in dy by dx, shouldn't we get the w value of w? Means, there was dy by dx, so dy by dx will be equal to w value, right?
no, you have not defined no x. X you have till you have not defined this require grad equal to true. If you put require grad equal to true, then only it will have the graph and it will compute. No, are you getting it?
Yes.
Yeah. So now, as like numpy, most of the functions you can use it here. So like numpy dot full here, np dot full here, you can use touch dot full. So it will create again, like I'll run it and show you. So this will be 3x2 matrix with 42 as each element. Okay, each element value is 42. Okay, so here you can do some concatenation. Okay. T3 and T6. Some sign up some value you can compute. Then this reshape function also works here. Okay. Now the intercompatibility with NumPy. So if you have done your written your code in NumPy and you want to do some deep learning application, you can directly convert it using like torch dot from NumPy of x, some variable you have defined or extracted some features using NumPy. Then you can directly write torch from NumPy of this one. You can directly convert it to this one. Okay. So the data types is this one. So this is, if you want, this is already in Torch, you want to back convert it to NumPy, because most if you want to save the values in some .NET format or something, it will be better to convert it to NumPy and do it. Okay. So some of the cases it is not compatible with Torch. Okay. So if you want to do some typecasting, some floating point 64 or floating point 32, you can do it. The number from 32 also. Your computational need. So that is all. If you have any doubt, you can take, or else.
So what is the difference between NumPy and Torch?
So the only difference is between NumPy array and Torch array. Torch helps you if you have kind of doing, if you want to do some backpropagation kind of thing for neural network or any kind of regression applications. So that stores the gradient value with the direction you are doing operations, but NumPy does not support that. That is the only difference. Otherwise, all are same.
Sir, how can I get the gradient value from that array torch array? Can you please?
Okay, so here you have seen no this y equal to wx plus b is a affine function. Okay, so I have defined w value and b value and x value, correct? Now in this case I am telling w and b are my weights and this supports gradient. Okay, so if you want to, once you have done this and if you put y dot backward, so it will automatically compute this gradient values. Okay, then once you see x dot grad, w dot grad and b dot grad, you can find this. As x does not support the gradient, as we have not written gradient is true, so it does not compute this when you are doing backward. So it is a detailed variable. Okay, so other cases you can get the variables values, gradient values. Is it clear now?
Yes.
Is it NumPy is a package and PyTorch is a platform?
No, both are as packages. Platform Python is a platform.
Okay.
Python is a platform. Both are packages. Like NumPy, PyTorch is also a package, library package, but it supports that gradient. It will store the in which direction if we go, no addition, subtraction, multiplications. So it will store that graph, and later when we do the backward, it will directly give the gradient values in that direction with respect to that variable.
PyTorch has extra facility compared to NumPy.
NumPy, yes. Okay, if there have no doubts, maybe you can close the sessions for today. Yeah, and we will meet tomorrow and at 2 p.m.
Jagbandhu, the off-topic question, but do
yeah, please.
you created any WhatsApp group or something for this?
We actually have a common WhatsApp group called IIT-DH events. Maybe if you want to, if you are not there, you can join.
Okay.
I think
Most of them who are there in the Tripoli Summer School or FDPs, they already have joined there.
So there's no separate group created for this?
No separate group. Okay.
Thank you.